Hey everyone, and welcome back to PrepFusion. So today we will start with the question series of double core, and the first subject would be power electronics. So in power electronics we have mainly four chapters: power semiconductor switches, then rectifiers, and then we have choppers, DC to DC converters, then we have inverters, uh, DC to AC converters. Correct. So these are the four topics basically that we have here. You can see here, right? So we will do the questions, we will do all the gate PYQs, but before starting I will highly recommend, please go through this revision X notes. So these are our short notes kind of thing for power electronics. So make sure, like, I think it is already present in the uh, video link, or just search revision X PrepFusion. You will get the video where I've explained what are revision X notes, or you can just go into the website under the free courses section. You will see at the last there will be a revision X short notes. So this kind of a short notes, you can see lot of stuff, lot of information is there. Quickly you can revise through all these notes. It's like 70 pages. In 70 pages all of the power electronics has been covered in a very good manner. So make sure you go through this and study from this, right? That will be hugely beneficial to you, and please revise and then only come to watch the question series. Otherwise you will not be able to solve the questions. So you watching me solve the questions will not give you any benefit. So make sure you revise the notes first, then you come back to the solutions. So yeah, before starting, again I want to say, if you are enjoying this series, hype the video, like the video, comment on below whichever concepts you found well. So we will try to use as little formulas as possible, like in choppers and rectifiers. In semiconductor devices we have used as low as possible formulas, but of course once we start with inverters there is the requirement of formulas. So in inverters we have used. So I'll be honest with you, wherever I use the formulas I will say you to, wherever I have not, like in choppers, rectifiers and power semiconductor switches, we have tried to use as minimum formulas as much possible. Like we have tried to derive everything in the question itself. So yeah, if you do enjoy, again, like, hype, subscribe, and obviously comment down below. So let's begin with the first chapter. Let's begin with the first chapter. So this is the first question, where they have told us that four semiconductor devices are shown in the figure below, with the relevant terminals, okay, marked. The devices that can carry DC current continuously in the direction DC current continuously in the direction shown when gated properly. So basically we will provide the gating properly, and they can the DC current can flow continuously. So first thing I know, this, right? If I gate the SCR, what do you know? The current can flow from anode to cathode. If I don't gate the SCR, current will not flow from anode to cathode. It is similar to a diode. Just a gating feature is there. And in diode, do we use our diode in reverse bias condition? That is, current flowing from cathode to anode as shown in the direction? No. So thyristor also, the current will not flow in the reverse direction. So if you remember, the VI characteristics of a thyristor was somewhat like this, right? So it was somewhat like this, but this curve we will get only after some gating, right? Otherwise we will not get this curve. If you remember, we had to, there was a latching current, there was a holding current, that's all. So yeah, so the thing is, we never operate beyond this region, because after this we know our device can get damaged. So this cannot this device cannot let the current flow in the reverse bias direction, not possible. Triac, yes, triac we know it is just an extended version of diode, extended version of SCR or thyristor, where thyristors are connected back to back, right, in opposite sense. So current can flow in both directions. I hope you remember this. So triac, yes, current can flow in both directions. What about GTO? Again, it is similar to gate turn on thyristor. So it is similar to thyristor only, and we know the GTO does not have bidirectional property. I hope you have went through the IV characteristics of all the devices. Very, very important. You must revise it. So GTO no, thyristor no. MOSFET, if you see, MOSFET is a symmetrical device. Actually, the drain and source can be interchanged. If you remember, drain and source can be interchanged if you have studied it, right? So MOSFET is kind of a bidirectional device, because it has a, what is this? If you remember, it has an anti-parallel diode built in, right? Anti-parallel diode. So generally we say that current can flow from drain to source, but current can also flow from source to drain, because it has an anti-parallel diode, as you can see here. Okay, so MOSFET is kind of a bidirectional device. It allows current in both directions. Triac allows current in both directions, but thyristor and GTO does not allow. So your answer will be option B, Triac and MOSFET. Let's move on to the next question. So mostly in switches, they mostly asked questions of theoretical in nature. So that's why the questions are not that difficult to solve. Let's try to solve few questions and we will see like how far we can go. A double pulse measurement for an inductively loaded circuit controlled by the IGBT switch is carried out to evaluate the reverse recovery characteristics of the diode. Okay, so don't worry about all this. The question seems pretty big, but don't be scared. Whenever the question is pretty big, right, the solution is more simpler. So just give me 1 second. Yeah. So what are the thing? D is represented by the diode approximated as a piecewise linear plot of current versus time. So this diode is approximated as the diode current versus time. So this is how the current is varying in the diode circuit. Okay. Okay. So current we know generally if it is marked as positive, that basically means current is flowing from P to N, right? Anode to cathode. So current is flowing in this direction. Okay. Cool. Where L parasitic is the parasitic inductance due to the wiring of the circuit and is in series with the diode. The point on the plot indicate the point on the plot, that is 1, 2, 3, 4, indicate your choice by entering 1, 2, 3, 4, at which the IGBT experiences the highest current stress. When will the IGBT experience highest current stress? At a 1, 2, 3, or 4? Okay, so that is what they are asking. Okay, how will it work? When will the current stress be highest? When will the IGBT experience highest current stress, right? So we know so this is my load, right? And this is they have they told me anything? Double pulsed inductance. So I will assume this is like a DC source, right? Because no sinusoid is drawn. This is a DC source. So we'll assume that this load takes some constant current, right? Because it's a DC source, and in DC the inductance can be shorted for the load. I'm talking about the load. So I'm assuming load is taking some constant current V by R always. Okay, from the source that is going always. Now this current is always V by R. Now here what is happening, initially this diode current is positive, right? Here let's say some 2 ampere or whatever, I don't know, but some positive value. So some current is incoming here, right? And IGBT again, it is like a BJT, it is not a bidirectional device, it is a unidirectional device, so current can flow only in this direction. Okay, so current is coming from here and here, ultimately they're getting added with KCL and it is coming outwards. Now when will the stress be maximum? The stress, what do you mean by stress? Highest current stress basically they mean when will the current across the IGBT be maximum. IGBT will be maximum, right? So when will the IGBT will be maximum? It will be maximum when the current that this is delivering is minimum, right? When this takes starts to take some current. So we see the current is reducing. Whenever the current will reduce, this current has to be constant because load, it will take some DC current, constant current. This is sorted, right? This current is reducing. It is going to 0 and then it is going to negative, right? Here let's say this is some -2. So now instead of the current being +2 to -2, how it is -2? So current will flow like this. Now you will say, sir, how is the current flowing like this? How is it -2? So uh, it it may be it is not exactly -2. It may be like it is somewhat very close to a saturation current, reverse saturation current, right? Because you might have a doubt, sir, how the current across the diode can be negative. Yes, you are correct. How can it be negative? But yeah, it will make some potential, somehow the current will flow in this direction and it will be very close to the reverse saturation current of the diode. So current is flowing in the here, right? So now the IGBT is delivering the load as well, is delivering the this branch as well, right? The parasitic inductance. Okay, and this is happening due to inductance only. Inductance is doing it. So now IGBT is delivering both the branches. So of course, current will be maximum at 0.3, right? Because the diode is also taking some current and the load, of course, it is taking some current. Who is delivering? IGBT. So stress at 0.3 will be maximum. So in this case, your 3 will be your answer. That's how simple it is. Okay, not that difficult. Yeah, so Just let me go to the third question. Now, this is a mathematical question. A charger supplies 100 watt 20 volt for charging a battery. Uh, Now, a battery, remember, is a DC load, right? Always remember, battery is a DC load. So if it's a DC load, your voltage also will be DC, and your current also you will consider the average current, because we know power is one DC power is V into V average into I average. That is what my DC power is. The laptop, the power devices used in the converter inside the charger operate at a switching frequency of 200 kilohertz. Okay, they operate at 200 kilohertz. At remember, 200 kilohertz is very high frequency. Okay, it's almost in the megahertz range, right? This is very high frequency. Which power this device is best suited for this purpose? Now, this again is a theoretical kind of thing. You have to remember that MOSFET is generally operated at higher frequencies. That's why everywhere you see all the transistors, everything is made with MOSFETs. And all our power electronics devices are made with MOSFETs. So in this case, as it is a high frequency device, we will use MOSFETs. Okay, bit of theoretical thing again. So again, we have a question. Switch diagram has been given. The semiconductor switch needs to block voltage V, so it wants to block the forward bias voltage basically, right? Whenever this switch is open, and carry current in both directions during on state. Which of the following switch combinations will realize this? So BJT can block forward voltage, and current can flow in this direction as well if properly biased, and current can obviously, due to this anti-parallel diode, current can flow in the opposite direction as well. So option A is definitely certainly follows the figure 1 and figure 2 combination. Let's check for this one. So here this is not proper, right? So so the BJT can let the current to flow in this direction from left to right, but the diode will block this current, right? So actually this device is not bidirectional in current, this is unidirectional, so not possible, right? Here again this device is not bidirectional. Why? Because now if I, let's say if I want the current to flow from this to this, right, this diode will not allow, although this diode will allow it, but this diode will not allow it, right? Again it is unidirectional. Here let's check here. So if I let the current to flow in this direction, what needs to happen? The current will follow this diode path, right? No problems. Now if I let the current to flow in this, if I want the current to flow in this direction, yes, the BJT will allow it, right? BJT will allow the current to flow. These two diodes will not allow it, and then this diode will obviously allow it. So this is bidirectional, that is certain. What about blocking of the voltage? So certainly I can block the forward bias voltage because this BJT can block it, this diode will block it, this will not block it, but these two are blocking it, no problems. And of course this is also blocking it. So forward bias voltage is blocked, right? So yeah, D again is a proper combination, proper semiconductor switch that can do our desired requirement. Okay, very simple switches, like you will not feel very difficult. All you have to do is just study the what do you say, the what I forgot, just study the VI characteristics or IV characteristics, correct? Let's solve the next question. This one. The circuit shown in the figure has reached steady state with thyristor T in off condition. The circuit shown in the figure has reached steady state. Okay, circuit has reached steady state with thyristor T in the off state. So in the steady state, thyristor T will be in the off state. Off state meaning no current will flow through it. So if I replace the thyristor with open circuit, right, at steady state, obviously what will happen? This will have a resistor here, this will be here, and there will be capacitor, inductor, something like this, right? Okay. Microfarad, right? Now assume that the latching and holding currents of the thyristor are 0, so it latches at 0 current, no problems. The thyristor is turned on at t equal to 0. The duration in microseconds for which the thyristor would conduct before it turns off. So when does the thyristor turns off? It's similar to diode, right? So because the latching current and the holding current are 0, that means it will turn off only when the current through it will become 0. What is the current at t equal to 0? As soon as it is turned on. It is an ideal thyristor. As soon as it is turned on, what will happen? The thyristor will be short circuited, right? And here I have my L and C. Okay, I will explain what will happen exactly. Now what is happening is some current is flowing. It is, if I close this loop, this is 100 volts, this is 4 ohms. So the current would be 25 amps. That is my current. Now this is the current that is flowing through the thyristor. Now what will happen to the C and L? That is what I want to know, because C and L also will work. Okay, it is turned on, holding currents are 0, lessing currents are 0, off state. This is 25 amperes. I'm just trying to think the duration mechanism for which the thyristor would conduct. Okay, we have this 25. The thyristor is turned on T equal to 0. Now, is this analysis correct? That is what I'm trying to think. The duration microseconds. So, remember one thing. Before this thyristor was turned on, right? This whole circuit was in steady state, correct? So, before even this thyristor was turned on, one thing I have just made a small error. Before this thyristor was turned on, the circuit was in steady state, right? So before it was open, because thyristor was off. So if thyristor is off and the circuit is in steady state, and we have R, L and C, and this is a DC source, so of course we know at steady state the inductor is replaced by short circuit. So this is, I'm talking about before T equal to this circuit, whatever I'm doing, this is before T equal to 0. Before T equal to 0, right? You have to study transition for this. Before T equal to 0, my C, what will be the voltage of C? This will be 100 volt, right? Because it will reach to steady state and your inductor will be replaced with short circuit, correct? So the capacitor will have all the 100 voltage. Now as soon as I will uh, turn on the, so here what will be the current would be 0, right? 0 ampere current. And as at T equal to 0, what will happen? The thyristor will be turned on, right? So it will be replaced with short circuit. So capacitor will still keep its voltage 100 volt, right? And inductor will still keep its current 0 ampere, right? So what will happen? But this KVL will be valid. This KVL will be valid because this is short circuited, no problems, right? So still this will have the current of 25 amperes. But slowly what will happen is, because this is 100 volts, right? And if I compare the volt, so let me assume that this is my VL of T, right? VL of T. If I apply KVL in this loop, I see that plus 100 plus VL, I am talking about at 0, T equal to 0 plus, right? So VL is equals to minus 100 volts. Okay, VL equals to minus 100 volts, right? So VL is minus 100 volts, which means that, so plus 100 basically means the current will it will energize, so more current will come into this. Minus 100 means current will go like this, right? More current will go like this. Okay, that's all it means. So hold on a second. Am I talking about the correct thing? Hold on a second. This plus minus VL. So plus VL minus 100. So this will decay. Okay. So basically it's so what is VL? VL is L DIL by dt. VL is L DIL by dt, which is negative. So current will reduce. Currently the current is 0 in this direction, if I'm not mistaken. So yeah, current will decay in this. Now in which direction it will decay? Yeah, so capacitor will deliver the energy, right? Yes. So current will decay in this direction. So current, some of the current will flow in this direction. Okay. Okay, that's not a problem to us. But this was the analysis. So current will decay and somewhat the current will increase here. But how will the function of the current look? Remember, if I just see this circuit in isolation, right? So till the thyristor is turned on, this circuit is always valid. This is a simple circuit. I have a C here that has initial voltage of 100 volt, and I have L that does not have initial current, right? And as the thyristor is on, this will be always shorted no matter what. Okay, this is L. Right? Now, can I write the expression uh, for the voltage across the, this is my VL, let's assume this is my VL, voltage across the capacitor? Certainly yes. So voltage across the capacitor will be, so it will be 100 cos omega naught t, right? Because yeah, cos will initially reduce, then it will go negative, then again positive. Yes, this will be 100 cos omega naught t. Why 100? Because at t equal to 0, I see voltage is 100. Then again you can check for other points, it will drop down only. What about the voltage across the inductor? Voltage across the inductor will be just the negative of this, right? VL will be minus 100 cos omega t. You can apply KVL, it will be minus 100 cos omega t. And we'll have to identify the instant when the current, so what is happening is through this, through here the current is always 25 amperes, right? Why is the current always 25 amperes? Till the point this side is turned on, this circuit is also always intact, right? This KVL. So this current will always be 25 amperes. So this current is always 25 amperes, right? This circuit is always intact till the thyristor is turned on. And from here, we can actually write the expression of the current, right? So, okay, supply, I don't know exactly how much current the supply is delivering. That, how do I calculate? So initially supply is delivering 25 amperes of current, because this is not delivering any current, right? All the current is coming from here. Okay, but I do not, okay, but yeah, okay, I know what is the current from the supply. What is the current from the supply? The current from the supply is this, right? Because this is the positive terminal, negative terminal, current always has to be 25 amperes only. It always has to be 25 amperes, certainly, right? So this input current also has to be 25 only, because this KVL is always intact. So this will be 25 amperes always. Okay, so this is 25 amperes, and let's assume that this is the current IL, right? And this is my SCR current. Now the thyristor will be turned off when, or naturally commutated when the current ISCR will be 0 or negative, right? When it will tend to negative. So what is my what is this KCL? If I write the KCL at this node, it will be, so I could have written the KCL at this node as well, no problems, but it's fine. 25 will be equals to ISCR plus IL. So my ICR will be equals to 25 minus I. Okay. Now we have to see basically when this current reaches 25 amperes, right? That is the point. So what will be my IL current? IL would be L DIL by dt, right? So L into DIL by dt. So differentiation of, okay, certainly something is, I'm just thinking. Okay, this is 100 volts. This will be cos. Will it be cos? I'm just thinking. It will be cos or something. So if you are ever in a doubt, right? So will it be cos or sine, right? Solve the circuit. Okay. It feels like I'm in a doubt and I'm in the exam hall. I will not take any risks. What do I mean by solve the circuit? Use Laplace. So you can replace this by 1 by Cs, and of course you can take out the voltage source plus minus 100 by S. So I'm solving it using Laplace because I feel because I have not studied this for a while, so I'm feeling underconfident. So now I will write the expression for current. Okay, now I am more comfortable because yes, there I don't know whether this is the voltage expression of the capacitor or not. Of course there is like there are formulas there which I have told you to remember, but if I don't know, I will not take any risks. If I don't know, I will not take any risks, right? Yeah. So this will be, IL will be in Laplace, IL of S 100 by S. So this is negative actually because this is in the opposite direction, right? So minus 100 by S upon 1 by CS. So this will be 100 C into, okay, I can take L also common, right? You can take L common. So this will be 100 into C by L minus 100 into C by L into okay, 1 divided by S square plus 1 by LC, right? So I'll just verify also whether the answers will come out same or not. So this will be right. So what is this actually? So I can multiply and divide by 1 by LC. So this is omega naught by S square plus omega naught. So that is, if I remember, that would be basically sine, correct? If I am properly remembering it. So S by S square plus omega naught, that is basically my cos. That is basically my cos, and omega naught, hold on. So if I'm multiplying, so this is omega naught by S square plus, that is, if that is my cos. So so we will do on the go. So sine omega naught t, this has, if I remember it correctly, it has omega naught by S square plus omega naught square. What will be cos omega naught t? So it is just the differentiation, right? If I differentiate this, and of course omega naught also will come in the front. Yes, this is correct. So yeah, if you ever tend to forget, right, just write down the Laplace terms. You will remember Laplace properties. You remember it. So sine omega naught t has a Laplace transform of omega naught by S square plus omega naught. And if you want to compute the if you want to compute the cos omega naught, you will differentiate this, right? And a omega naught term will come outside. So if I differentiate in this, of course, I have to multiply by S. And of course, a omega naught term has come outside, that omega naught will be cancelled. So ultimately, this will be my result. So I hope you have covered Laplace. So from that, you can take the intuition. So this will be actually, so I will have to multiply and divide by omega naught as well, that is under root L by C. So I will have to multiply and divide by under root L by C. This will be multiplied by under root LC. Okay, so under root L by C. Is everything okay? Yes. Just let me check. I'm multiplying this by S and taking L common, right? I'm taking L common, multiplying by S on both sides. Oh, this C will not come out, only L will be there. Sorry. I'm just taking the L common, right? C is there as it is. So now this is proper. Now this will be minus 100 into under root C by L. If I like take the Laplace inverse now, if I take the Laplace inverse now, right? So the question is becoming lengthy because I am not remembering the results. I am solving with basics, everything with basics, right? Not remembering the formulas. So this will be sine omega naught t, which is sine t by under root LC. Omega naught is under root 1 by under root LC. Correct? Now we got into the correct proper state. Okay. Now this is my current expression in time domain. So let us prove it. Let us prove it here as well. Okay, maybe I'm making some mistake here. That is because here the current is coming out to be negative, which is supposed to be coming out as negative only. LVL equals to LDIL by dt. I've already considered the direction of the current, right? So LDIL by dt. It's not minus. What am I making mistake? That is what I'm thinking about. Maybe this is not sinusoidal. That is where I'm making mistake. Maybe this is not. Okay. Because there will be omega naught as well. L also will be there. Let's see. Oh, sorry. Okay, what am I doing? I need to find out the current, right? Okay, why am I using this expression? I need to find out the current. So I already have this, right? I already have the capacitor voltage. Why am I fighting so much? So my what is my capacitor current? Capacitor current will be IC or IL, whatever. IC will be equals to IC of t, right? IC of t will be what? In this direction actually. Remember, this is my IC of t direction, which is same as IL only. So IL will be equals to IC because they are in series. IL of t. That is what I was thinking. Where am I making the mistake? That is equals to C dVc by dt. C dVc by dt. So voltage I know. If I differentiate this into C, so this will be 100 C omega naught into sine omega naught t. Okay, so this will be IC of t. Omega naught is what? 1 by under LC. It is the resonant frequency, natural frequency. So this will be minus 100 into under root. So if you replace omega naught with under root 1 by under root LC, this will be sine omega naught t, that is t by under root LC, which is the same expression that we derived with Laplace. Okay, so yeah, you can solve with shortcut as well instead of doing Laplace, but just to be safe in the exam hall, I like to be safe, so I solve using this. So it might feel like I'm taking so much time in this question because I of course we gotta solve it in seconds here, right? But I don't want you to remember formulas. I want you to understand both methods, the basics and formulas. So previous questions mostly were theoretical, so those will not take you much time. So you save time there, you utilize that time here. Okay, so yeah, now this is fine. Now we got the current expression. So basically we have to identify when this current will go negative. So when this current will be minus 25, right? When it is minus, so my ISCR, when it will be 0 at that, when it will become first time 0, right? At that moment of time, the SCR or thyristor will turn off because the holding current is also 0 amperes. The holding current is also 0 amperes. If you don't understand what is holding current, latching current, you have to watch, you have to go and watch the revision X notes. There all those things have been explained in a very proper manner. Okay, so that is fine. So what is C? C is 1 micro, L is 4 micro, so this will be minus 100 under root 1 by 4, that is by 2. This 1 micro, 4 micro, so this will be again under root 2 micro holes, so 2 micro actually. Okay, remember this is 2 micro, that's all, because L is 1 micro, C is 4 micro, so it is 4 into 10 raised to the power minus 12. If I do the under root, it will be 2 into 10 raised to the power minus 6. So that's how you have to be efficient in the calculation. Don't always try to use the gate calculator. Without the gate calculator, try to solve it. So yeah, that is it. So this will be minus 50 into sine t by 2 micro. Now when this will become minus 25, the moment this will become minus 25, when is I say 0, the moment my IL is equals to, okay, sorry, this will not be minus 25 initially, this will be plus 25, right? The moment my IL is 25, plus 25 actually, so it has to be equals to plus 25, right? So basically my sine t by 2 micro has to be equals to minus 1 by 2. Remember, it is negative, not positive. It is negative, right? So when will it be negative? When will it be negative? So when is my sine graph minus half? Do you remember? So I'm only talking about t greater than 0. So sine t, I'm plotting sine t. I don't care about omega naught for now. Okay. sin t by capital T, you can do it actually, or sin omega naught t, or just let us just plot t and then I will explain. So this is nothing but the inside thing is, let me plot sin theta. The inside thing is nothing but the angle basically, that's all. So when is my sine minus half? When theta is positive, right? So the graph of sine is something like this. So sine will be minus half somewhere here, because here sine is minus 1, correct? So this is pi and this is 3 pi by 2. So sine will be minus half 30 degrees after this, right? Because after 30 degrees from 0 we get half, correct? We get plus half. So this will also be symmetrical. So after 30, that is pi plus pi by 6 radians, this is the point where my sine will be minus half, or you can now you can use the calculator. You will do what you will do, you will do sine inverse in the calculator, you will do sine inverse of minus half, okay, in radians, and you will see, you will in radians, make sure you make the angle to radians and you will get this value, okay. So but we already know this. So my t by 2 pi, sorry, 2 micro will be equals to 7 pi by 6. And what have they asked you? What have they asked you? Hold on, this is 7 pi by 6. Yeah, what have they asked you? They have asked you, remember, to see the units as well, right? In the duration in microseconds. So it is already in micro, so I don't need to do any conversion. Already it is in micro only. T, this bottom side was in micro only, right? It was already in micro. So we'll just take the 2 on that side. So your t will be 7 pi by 3 microseconds, right? So you will have to only calculate 7 pi by 3, that's all. Okay, you don't need to do any conversions. Don't need to do any conversions. So this will be 7 into pi by 3. So this is equals to 7.33 microseconds. This is the answer. So yeah, this question took more time, but it's okay. You can give more time because you already saved the time on the previous questions. So this question was very good question, and I'm expecting a question like this to be asked. Okay. So yeah, if the following switches devices have similar power ratings, which one of them is the fastest? So of course MOSFET, we know MOSFET is always the fastest device. It is a high frequency device, high frequency switching devices. So if they have similar power ratings, MOSFET will have the highest switching frequency, and it will be the fastest. Option D is the correct answer. So with this, we are done with the first chapter. Now we will move on to the second chapter. Let's begin with rectifiers. So this is the first question. A single phase full width diode rectifier is fed from a 230 volt 50 Hz sinusoidal source, which supplies a series combination of finite resistance and a very large inductance. So if it is a very large inductance, right, then the current will always be constant. Let's assume that current is some IDC current. Okay. The two most dominating frequency of the source. So I will have a I will not draw the full bridge rectifier here, but I will have a full bridge rectifier. Okay, and here is my source, sinusoidal source, right? 230 volt 50 hertz. Okay, now they are asking me what will be the current, like what will be the most two dominating source currents. Now you will feel, sir, I have a DC current, so of course the DC, there will be some DC in the source. No, that was the advantage of full bridge rectifier. I hope you have seen the revision X notes. There everything is mentioned properly. In full bridge rectifier, what components are present, what is the graph of source current, everything is mentioned. So if it's a DC current, right, so although in the load side the current will be constant, that is IDC, in the source side, because it's a full bridge rectifier, so this diagonal, right, these two diodes will conduct for one half cycle, and these two diodes will conduct for the second negative half cycle. And once these conduct, the source current direction changes, but the load current direction remains same. I hope you remember these things. So that's how you're revising, right? So in the positive half cycle, current will be positive. Again, in the negative half cycle, again current will be negative, positive, negative, right? That's all. That is what will happen. Okay. So yeah, this will be omega t. This will be V. Okay. So yeah, not V, sorry, this will be current, source current, right? So source current, now this is not a pure sinusoidal, right? So of course it will have a fundamental frequency. If I write down the Fourier series expression, it will be what? 2 into peak to peak. What is a peak to peak? This is IDC, this is IDC. So 2 into peak to peak. So 2 into 2 IDC upon n pi into sine n omega naught t, where omega naught is the fundamental frequency, basically summation, and it will be half-wave symmetric, so it will contain m equals to 135, n equals to 135, and so on till infinity, correct? So yeah, that is what will happen here. So of course, what is the first component? Fundamental component, that's omega naught. In frequency terms, it is f naught, so it is 50 hertz. 50 because the source has the sub frequency 50 hertz, so fundamental component would be 50 hertz. Then it will contain 3 omega naught, 3 f naught, 150 hertz. So these are the most dominating. So because if you see, if I increase n, the magnitude is reducing. This is the expression of current, right? Fourier series expansion of the source current, Is of t. So if I increase n, this magnitude will be reducing. So the two most dominating frequency components in the source are 50 hertz and 150 hertz. That is option C. So option C will be the correct answer for this particular question. Okay. So yeah, let's solve the next question. A single phase full bridge rectifier is fully controlled thyristor rectifier feeds a load comprising of 10 ohm resistor and a very large inductance. The rectifier is fed from an ideal rectifier is fed from an ideal 230 volt 50 hertz source through cables which have negligible internal resistance and total inductance of 2.28 millihenry. So you understood already that this is a question of source inductance, right? So I will have a rectifier here block, I don't worry about that, and I have a source inductance actually LS, that is 2.28 millihenry, and I will have a source that is there. Now what are they asking? If the thyristor is triggered at alpha equals to 45 degrees, what is the commutation overlap angle? So commutation overlap angle basically means this. So what happens actually? So if let's assume that if this inductor was not there, if this inductor was not there, source inductor, I mean the source inductor, if the load inductance is very large, that what means what? That basically means that my load current will be almost constant. Load current will be almost constant if the load inductance is very large. So the source current, if the source inductance was not present, if the source inductance was not present, the source current would look something like this. Okay, this will be, if I write it in terms of time, this will be capital T by 2, this will be capital T, and so on, right? Now minus a plus I, right? Okay, so now what we can do is, if the source inductance is present, it will not allow this sudden change, right? Because inductance does not allow sudden changes. So what the inductance will do is, there will be a bit of overlap. What will happen? What do I mean by overlap? I will explain. So what happens? So when this current is positive, source current is positive, then what happens? The first group conducts, that is D1 and D2, if you remember in the graph. So let's draw the rectifier basically, so that will be more clearer to you. So this is my supply. Do we have any rectifiers? This is just a, okay, they have never, this should not be there. They've never drawn, okay, yeah, this is a simple bridge rectifier, right? Yeah, that will be more easier for us to use instead of, so yeah, best example, we have got a rectifier. So yeah, so if you see here, right, what is happening? This is without the inductance I'm talking about. So let's assume that this is my T1, this is my T2, okay, this is my T3, this is my T4, right? So in the first positive half cycle, this will be the path of conduction, right? So D1 and D2 are on, you can see. The negative half cycle, current will flow in this direction for the source. It will come here, go to the load. Load still has the same direction of current. It will come back from D4 and it will come back, right? So the direction of current in the source has been reversed, but in the load it is still intact, it is same. So that is the advantage basically. Now what happens is, because the current is changing, right? If there is some source inductance, the inductance will not allow this sudden change of current. So just before this and just after this, the inductors will smoothly change. The current across the inductor will smoothly change. So I can draw it actually. So this will be somewhat like this. So it will not suddenly go from minus I to plus I. It will go smoothly. So this will be plus I, right? Then again at T by 2 exactly the current will be 0, right? But just before T by 2 and just after T by 2 the current will start to reduce like this. So at T by 2 current will still be 0, no problems. And here again the current will be minus I. Okay. Now the interesting fact here is that, what is the interesting fact here? The interesting fact here is that they are asking me what is the overlap angle. What do they mean by overlap? Overlap basically is this angle, this right, this is called as mu, overlap angle. If you have studied, you will know about this. What does it mean? It means during this phase, right, all four diodes actually will conduct. All four of them will conduct. All four of them. So because bit of current will start to flow from D3 slowly. So this I have taught in my full course. This I have taught in the revision X notes. You can see the notes there. At this moment of time, when this current is reducing, all the four diodes will conduct. That's why it is called as overlap, because diodes are overlapping each other. Okay, due to the source inductance. Because who is doing it? The source inductance is doing it. I have to calculate this angle. Now there is a very good formula for this. If you want to remember it, you can remember it, or how else can you solve it? So we can use bit of basics here. What is the basics? The basics is, so when this overlap happens, right? So all four diodes are on. If all four diodes are on, so basically this is essentially short circuit. So why all four diodes will start conduct? So let me explain you why it will conduct. So let's say I have D1 and D2 here, right? D1, D2, because this is the point where both D1, D2 conduct, that is same. Now as soon as you see the current starts reducing, if the current starts reducing, that means the current across D1 and D2 will start reducing, because that was the path of the current. So this current is reducing, but certainly the load current is constant. DC, it is constant, right? Because it has a high load inductance, so this will be constant. Now if this current is reducing, this current is constant, so this D3 has to turn on. Who will turn this on? The source inductance. So this current will be on. Similarly, same concept you will apply here. This diode D4 also will be turned on. That's why it is called overlap, because all four diodes are on. All four of them are overlapping at the same time. That's why it is called as overlap angle. Okay, that was the concept regarding overlap angle. Now what are they asking? They are asking me the overlap angle in degrees, right? So how do I compute the overlap angle in degrees? So there is a formula that you can use, but let's try to see if I can do it without the formula. Okay, let me try to think. If I'm like I have derived this with basics in my full course, so let me try to derive here itself bit of things. So when this diodes are on, right, what is the voltage across the load? The load voltage. So previously if the load voltage was this, if you see, load voltage was this always. Okay, I will not explain everything here, but you get the point. But once the diodes are turned on, right, the load voltage is this, omega t, the load voltage will become something like this. Whenever all four of them are overlapping during this point, right, till this point, the load voltage becomes 0 actually. So this is 0, then again this will certainly change. Voltage can change certainly, no problems. Then again it will be 0 for a while, and then again it will suddenly increase, then again it will reduce 0, like this, right? Okay, So that is the load voltage. Now what I want to calculate, I need to calculate the this mu angle. How do I calculate this mu angle? So I'm thinking of something. I know this very basic equation, right? So my VL equals to L DIL by dt. Okay, VL equals to L DIL by dt. So what I can do, I can take this dt on the other side. Okay, VL dt equals to L DIL, and I can integrate this area. VL dt equals to integration of L DIL, right? And IL is changing from plus I to minus I, correct? Plus I to minus I. So this will be 2 into I into L, right? So it is going from plus I to minus I actually. Okay, this will be negative, that is fine. So this will be minus 2I. Minus 2I into L. What about VL? What is the so VL is what? VL is basically the voltage across the source inductance. So I'll have a source inductance here. That is what my VL is, right? That is what I've written over here. So VL is Vs minus VO, correct? Whatever is the voltage. VO in this case, because these diodes are shorted, it is 0 during this derivation, right? VO is 0, so it is equals to basically VL equals to Vs minus the voltage VO, and we know the diode is shorted, right? This diode is shorted, so VL essentially is Vs only. VL essentially is Vs only, right? Because these two diodes are shorted. So if I apply KVL, I will see I can simply apply KVL here, right? These two, okay, no, hold on. So I can apply KVL like this. Yeah, you can apply KVL like this. Here, yes. We can simply apply KVL like this, right? Hold on. This, we can start from here, we can go here and here, right? So VL is nothing but Vs only. Okay. From where I'm going. So this is what point? This point is what? This point is actually, so this is symmetrical, right? So this will be pi by 2. So if I write this this is written in terms of time. Okay, time is also fine, but we have to write in terms of omega, actually that will be best. Okay. That will be actually best. Yeah, this is dt, right? Oh, let's not write this in terms of omega, let's write this in terms of time only. So this is angle actually, remember your mu is in degrees. Okay, mu is in degrees, right? And okay, this is, we have alpha as well, don't forget. Okay, I forgot we have alpha as well, right? Okay, sorry, we do have alpha. If I have alpha, then how will things be? If I have alpha, okay, current graph will not change actually if I have alpha, but voltage graph will change a bit. So voltage graph, right? If I had a alpha, the voltage graph would be like this. So if we have a alpha, right, alpha, then there needs to be a freewheeling diode as well. There needs to be this as well, I'm guessing. Yes. Oh no, let's, yeah, there needs to be a freewheeling diode. So for a control rectifier without source inductance, this is the voltage. So I will not explain because again out of scope. Please go through the notes. So yeah, just one small thing. So if I have firing angle alpha, right, so everything will be delayed by alpha. So this graph will start from alpha, this will be then like this graph will start from alpha plus mu. That's the difference, that's the only difference. Okay, so these things unfortunately you will have to you have to like understand and remember basically, because you'll not derive every single thing in the example, right? That's impossible. So this will start from, so what essentially happens is that yeah, we will integrate from alpha to alpha plus mu, that's all, from alpha to alpha plus mu. So the point, so what will happen, everything will be delayed actually by alpha. So what will happen, I can shift this here, so it will not, so if I draw in, if I plot in omega t. So the reversal process will start from alpha, because that is when the other diodes will be triggered. So other diodes, the D1 D2 are triggered at alpha, right? That is when the current direction changes, if you remember. So yeah, one thing will change, because if inductance is not present and if my firing angle is alpha, then what will happen? The reversal will start at alpha only, because at this point the thyristors, although I was talking about diodes, right? If I change them to thyristors, so at this point T1 and T2 are triggered, then they will be on, right? Then the current direction will reverse. Okay, so you have to go through the full bridge rectifier once. I was explaining the basics, that's why I have taken the diodes. But if thyristors are present, then thyristors will turn on when they are triggered, right? Without the source inductance. Now with the source inductance, if the thyristors are triggered, the current will not instantly change from the source, right? They will slowly change. That's why there is a delay of mu. So this is alpha and this is mu. That's why there is a delay of mu. Okay, so we can solve it from here as well, right? So this is my current and this is my voltage basically. So alpha to alpha plus mu. This is my VO. So my VO is 0 from alpha to alpha plus mu, correct? So it will be equals to Vs only. From alpha to alpha plus VL will be equals to Vs only. VO is 0 from alpha to alpha plus mu. Now what about the time? Time would be, it will be alpha by omega naught, correct? Because omega naught into t is basically my alpha, right? Alpha by omega naught will be my time in seconds. Okay, because alpha is in, you can write alpha in degrees or radians. For now I am considering alpha to be in radians. Okay, so I will start from alpha by omega naught. Sorry, will I start from alpha by omega naught? Sorry, this will not be alpha, this will be pi plus alpha. This is not alpha, this will be pi, this will be pi plus alpha. So you have to unfortunately remember how the graph looks. This will be pi plus alpha plus mu. So this part, right, is pretty difficult for me to compute. So I have to integrate from pi to pi, alpha plus mu plus pi. What I can do, I can take a simpler case. I can start from 0, omega equal to 0, or t equal to 0 to t equals to alpha plus mu. Okay, that is the easier part for me to compute, because in this duration what is happening? Hold on, not in this duration. Sorry, I will not. So this is 0. This will be 0 from, this will be alpha, right? Yeah, somewhere between there will be alpha, and after triggering of alpha, okay, my graph is pretty congested. Let me try to keep it more. Okay, let me explain you what is happening. Otherwise you will get confused and you will just shout at me, sir, what is happening? I'm not understanding. Oh, cool. So whatever I discussed previously, that was with the diodes. But what if I have a firing angle? So for a firing angle, this part I hope is clear, right? This is how my voltage will look without source inductance. Without source inductance. Now if source inductance is involved, if the source inductance is involved, what will happen? Even if I fire here at this point, the current will not instantaneously change. They will change slowly due to the source inductance, right? So they will change after a delay of mu, that is called as the overlap angle or the delay angle. So if I trigger at alpha, what will happen? Due to overlapping, all 4 diodes will be on, and if all 4 diodes are on, the load voltage will be 0, and if load voltage is 0, that basically means that the current will slowly increase, right? So there will be delay of mu. So what will happen? This thing I have to integrate till this point, because this is the point of transition. So this time my current is not going from plus I to minus I, it is going from minus I to plus I. Okay, I hope that part is clear. So it is going from minus I to plus I. Okay, this is more easier for us to calculate. And what is my angle going? So my angle, Vs angle, right? Vs, where Vo is 0, that is from alpha by omega naught to alpha plus mu by omega naught. Remember, why is omega naught? I am converting it into seconds, because here I have dt, not d omega naught. I have dt. Just be careful. Now the simple thing is, I can easily directly write the formula and you can solve it. That's it. It will be a 2 minutes question if I directly use the formula. But I don't want to do that. I want to do something different, right? I don't want to mug up, like, of course there are formulas, you will have to mug up formulas, but I want to minimize it as much as possible. I want to do conceptually. That's why I'm wasting this much amount of time. So this will be alpha by omega naught to alpha plus mu by omega naught. Okay, so this will be plus 2IL. Now this is much easier, right? So VO is 0 in this whole region. So it is simply Vs. Vs is Vm sin omega naught t. That is given, right? Vs is So it is like sinusoidal source 230 volt Vm sin omega naught t into dt alpha by omega naught to alpha plus mu by omega naught, correct, equals to 2 into I into L. So here I will directly derive the formula actually. So most other places, most other coaching institutes, they will just directly write the formula, whatever I am deriving here, right? They will not explain you anything. This much I am explaining you the concept. They will not explain these things. So Vm by omega naught integration will be minus sign. So minus sign that will come first. So this will come first. So this will be cos of alpha minus cos of alpha plus mu. This is equals to 2I naught, sometimes they write as I or IL to L. So what is, so this is my expression. So from this expression I have to solve and I will get the value of mu, the angle, the overlap angle. But for that I need the value of I. L I know L, I know 2, I know Vm, I know omega naught, I know alpha, everything I know. I just need the value of I. So I is the DC current basically, right? I is the DC current. So when so DC current we can find, it does not matter whether inductance is present or not. So what is the DC current? DC current will be simply the average current across the resistor, right? So what will be the DC current? DC current will be V average by R, because your your VL average will be 0. So the your VO will be VO average will be equals to VR average, right? That is what a DC current, because it is a constant current. These things I have discussed many times. What is VO average? So V average will be nothing but that the average voltage here in this case, right? What is the average voltage in this case? Average voltage in this case would be, so in the load side you will always see that the voltage is starting from 0 from alpha uh, okay, hold on. Yeah, it will be 0 from alpha to pi on the load side. Yes, alpha to pi. But after alpha this will suddenly increase, but this time here this will reduce. So what happens is slowly this actually reduces by a bit the average voltage actually. So average DC current also will reduce actually. That is interesting. So what we assume, so actually what happens is the current, right, constant current is V average by R. So when the load inductance is considered, inductance is considered, then uh, we say that the average voltage also has been reduced by a bit. So with that, yeah, that will help us actually. Let me just see one thing. This will be, what will be the average voltage? Average voltage in a cycle, right? Average voltage in a cycle, V average when the inductance is considered. So I hope you know how to compute the average of this waveform. This will be 1 by pi, because I'm considering a V half cycle. I'm starting from alpha plus mu to pi. VO will be equals to Vm sin omega naught t d omega naught t, right? I'm integrating with respect to omega naught only, d omega naught t. Okay. Yeah, if I compute the average of this will be cos of alpha plus mu plus cos of pi is minus 1, that is 1 only, divided by pi into Vm. Yeah, Vm will be there, divided by R. This is equals to my current. Now what happens is, I think we do some approximation here that the mu angle will be much smaller, but do I really need to do this approximation? That is what I'm thinking. This will be my I current, right? Okay, I don't think we need to do this approximation. Do we really need to? No, we don't need to do this approximation. Yeah. So what I can do, I can replace my I, whatever expression I got for I, right? I will replace it over here. So this will be my I, correct? So if this is my I, okay, into L, and this is also Vm by omega naught cos alpha minus cos of alpha plus mu equals to this. So Vm will be cancelled, R will be there. Okay, so this will be cos of alpha minus cos of alpha plus mu equals to, so omega naught is nothing but 2 pi f. So this will be 2 into pi upon r. Pi will be cancelled. So 2 pi r and L into cos of alpha plus mu plus this will be omega naught, not omega naught, sorry, 12 by r. That's all. So I think we're almost at our solution. So this 12 by r will go on that side. This will be cos alpha. The Vm is cancelled. Omega naught is gone there. That is okay. Sorry. Don't forget the f. F is also here, right? 2 pi f. So omega naught is 2 pi f. F naught basically. F naught. So yeah. So that is there. So this will go there. So what is cos alpha? Cos is 45, right? Alpha is 45. Sorry. Cos of 45 degree. I'm just thinking whether everything matches up here. This is, yeah, I think everything will match up. This will be equals to minus 2 into L. How much is the source inductance? So this L, right? So this L is actually the LS, source inductance. This L is the LS. I forgot to mention. L is the source inductance actually. So this will be 2 into, so what is my R here in this case? R is this 10 ohm and L is 2.28 millihenry. So R is 10 into F naught. This is equals to 1 plus the same thing, 12 F naught by R. That's all. So this will be 2 into 10, 2.28 into cos of 45 plus mu, right? So I think we're almost there. Bear with me. This was a lengthy question, but bear with me a bit. So this will be 2 into 2.28. Okay, into 50 was also there, right? Don't forget into 50. 2.28 into 10 raised to the power of 3 divided by 10 into 50. 2.28. Then this plus 1 by root 2. Yeah, this comes out to be 0.68. 0.684. This divided by, so this is like, this value is minus 0.0228. Okay, so yeah, this will be 0.0228 plus 1. So here I have 1.0228, that is equals to cos of 45 degree plus mu. Okay, so I will need to calculate this value. This into 0.684, cos inverse of this comes out to be 48. So 45 plus mu is equals to 48.029 degrees. So if I subtract 45, this will be, your mu would be 3 degrees. Okay, approximately 3.20 degrees. This will be your answer for the question. Now in few places I have seen like they're given the answer as 4 because they were doing some approximation. What approximation? So they found out the value of I naught. with assuming that I think they did not consider this mu while finding out the I naught, but we have derived it. So everything whatever you have solved is correct. Of course, yeah. So there is this formula, direct formula. So this is the formula actually. This is the formula. Okay. So if you want, you can use the formula directly, but it's good to know how to derive. So even though I have not taught this, again I have derived this thing. So if you are confused, just rewatch this again. Just rewatch this again. I think whatever confusions are there, most things will be cleared. So initially I solved for simple diode rectifier, and then I improved it to thyristor. In thyristor, nothing will happen. Everything will be deleted by alpha. That's all. So let's solve the next question. Now this question is pretty interesting actually, and for this things, few things you should know that I will tell obviously. So a thyristor T1 is triggered at angle alpha. Cool. Thyristor T2 is triggered at angle 180 plus alpha. So this is triggered at angle alpha, and this is triggered at angle 180. Plus alpha. In each cycle of the sinusoidal input voltage, uh, assume both thyristors to be idle to control the load power over the range 0 to 2 kilowatt. So the load power will be in the range from 0 to 2 kilowatt, right? What is the maximum range of variation of alpha? Few things to note here. If I put alpha equal to 0, right, will this be controlled? No, this will not be controlled. This will always be turned on, right? This will always be short circuited. In that situation, what is the power? Can you tell me what is the power? The power will be simply Vrms whole square, or okay, power would be, how do I compute the power? It will be Vrms into Irms cos phi, right? Okay, so we can assume this to have a load that is a RC load, right? R and C. Okay. Okay, this has a load of R and C. Now this has a load of R and C. So how do I calculate this? So current, right? Your current would be IRMS current would be your voltage RMS upon the impedance, right? Z magnitude, that is 20. That is 20. It's 20 amperes. So your power would be, so what is R? If I assume it to be series circuit, it will be 10 cos 60, that is 5 ohms. So your power comes out to be 20 whole square into 5. So it is 400 into 5, that is 2000. That is coming out to be this, right? Which I don't want. Now few things to note here. If, so let's assume that this angle is phi. Okay. If actually, okay, I think they have made a bit of mistake. This should be plus 60. That's what I'm thinking. This should be plus 60. This is not minus. There is a bit of typo. Now, if this, it's better if you remember it. If you trigger your SCR alpha before phi, then this will never be controlled. This should be uncontrolled due to the inductor. Because this should be actually, sorry, this should be plus 60, not minus 60, plus 60. Okay. And even if it's capacitive, then also you have to consider the relation between alpha and phi. So if you trigger your SCR before this phi angle, phi in this case is 60, that is, if you trigger your SCR before 60 degrees, then your device becomes uncontrolled because the inductor itself has enough energy stored so that it can drive the load when the source is negative voltage, so that it can make the thyristor on. Okay. So if alpha is 60, it is uncontrolled. So in uncontrolled case, the power is 2000, but I don't want that, right? So basically your alpha must be greater than 60. Now what is the upper limit of alpha? So if your alpha is equals to 180, right? Upper limit of alpha is 180 only. So if your alpha is 180, because for the first half cycle I control this, then in the next half cycle I can control this. If alpha is 180, this thyristor never turns on, right? Because as soon as it will become 180, this voltage will be negative, hence this T1 will be not on, right? Even if I trigger it, the voltage will be negative across it, it will not turn on. And this T2 will be turned on at 360. 180 plus 180 is 360. So this T2 will be again not turned on, because again at the moment of time the voltage across this thyristor will be in reverse mode, right? So this will not be turned on. So there will be no power. So if I increase my alpha beyond 180, power will not be there. Okay. So the range of power from 0 to 2 kilowatt will be from 60 to 180. That is the range for alpha. I do understand that this information you need to remember. Yes, you need to remember it. You can look it up, search like in the Fourier series also. This particular phase shift comes, but it's good if you are able to remember it. This is a very small concept and it's not that difficult for you to remember. Let's solve the next question. So we have this next question. A single phase full bridge diode rectifier feeds a resistive load of 50 ohms from a 200 volts. Okay, so it is feeding a ratio load 50 ohms, 200 volts. If the diodes are ideal, the active power in watts drawn by the load is, it's very simple. It's a purely resistive load, then it is not even that difficult. It will be VORMS whole square by R, correct? And if it is a full bridge rectifier, your VORMS will be equals to your VSRMS, right? Why? Because your load voltage will be somewhat like this. So this is your source voltage, correct? This is your source voltage, and this is your load voltage. This, right? It is also sinusoidal, but not purely, right? But in RMS, what do you do? We square it. So if I square this graph and if I square this graph, both of will be identical. Both of them will be identical. So RMS values will be same. Although the exact voltage graphs are not same, RMS value will be same. So this is very simple. This will be VS RMS by R. VS RMS is 200, right? So if nothing is mentioned, you will assume this to be the RMS value. 200 by R, 200 whole square by R, that is 50. So this will be 4 into 10 raised to power 4. That is 50. That is equals to okay, this, right, 48, and 1 0 is here, another 0 is here, 100, 800. Yeah, 800 watts. So 800 watts would be your answer for the question. Pretty simple, pretty straightforward, not that difficult. Let's solve the next one. So read this question. You can include this to be network theory, AC part, or into this as well. That's both will work. The voltage at the input of the AC to DC converter is this sinusoidal, right? Where omega is this. The input current drawn by the rectifier, the input current or the source current drawn by the rectifier is this, right? Like the rectifier is here, then there is load, and then there is the input, right? Like the supply. So the input current drawn by the rectifier is this. So this is basically the source current. What is the input power factor? How do I compute the input power factor? So what is source power factor? Do you remember what was the formula for power factor? It is the ratio of the active power to apparent power. So if I'm computing the source power factor, it will be the source active power by the source active power by the apparent power, right? So yeah, so what is the source active power? You can easily compute, right? This is my voltage, so only the same frequency terms will contribute to active power. These things have been taught, so I will not explain here. So this will be VRMS. I'll solve this directly. VRMS into IRMS, that is 10 by root 2 into cos of theta. So angle between this and this, right? This frequency component, that is pi by 3, cos of pi by 3. I'm not explaining this because this thing I hope you know already, right? How to compute the active power for multi-tone signals. Divide by the apparent power. Apparent power is something else. Apparent power is VRMS into IRMS. Okay. So what is VRMS? It is very simple. It is 230. like basically 230 root 2 by root 2, that is 230. What is IRMS? IRMS will be this RMS whole square plus this RMS whole square plus this RMS whole square whole under root. I hope you know these things. If you don't know, you need to revise. So IRMS would be IRMS would be 10 by root 2 whole square plus 4 by root 2 whole square plus 3 by root 2 whole square whole under root. So let me compute this value. Cos of 60 is half. Okay, this whole under root, that comes out to be 28, which is actually a lot. This should not be this much high. Why is this high? Hold on, let me compute this again. So 10 by root 2 whole square plus, okay, 4 by root 2 whole square, that is 16 by 2, that is 8 only. That 16 by 2 is 8 only, plus that is 9 by 2, that is 4.5 whole under root. Okay, this comes out to be 7.8. That's what I was thinking. 7 point. So this will be into 230. .3. So yeah, that's all. And the top will be 230 into 7.07 into cos of 30, that is 0.5, right? So this will be 813.05. Let me just check whether I'm doing everything correct or not. I guess yes. This divided by 1818.3, that comes out to be 4.477. So of course there is some formula, you can use the formula, but I will not use the formula. Okay, I will not use, because anyways this will get cancelled. This VSRMS will be cancelled. Ultimately this is the important part. Okay, this SRMS and the fundamental component into the power factor. Like fundamental, this is called as the fundamental power factor. I don't want you to remember all these things, just this much is enough. Input power factor, how to compute this with basics. Let's solve the next one. So we have a ideal AC to DC rectifier circuit. A load current magnitude is constant, ripple free. The thyristor are fired with the delay angle of this. So don't get confused with the overlap angle. Okay, so yeah, sometimes nu is also called a delay angle, but don't get confused with that. This is called as firing angle. The amplitude of the fundamental component of the source current in amperes. So what will be the amplitude of the fundamental component of the source current? So again, if it's a simple circuit, right? So you know the Fourier series, how will the Fourier series look like? So we don't have any source inductance, so it will be this, right? So I will start from alpha. Hold on a second. The graph will be somewhat like this. So alpha, then pi plus alpha, then again 2 pi plus alpha, and so on. Right. So this is I. Now the Fourier series for this is how I remember it. It is 2 times the peak to peak. So 2 times 2 IDC upon n pi into sine n omega t minus n alpha. This also will be there. Okay, this also will be there. Now they are asking me, so n will be 135. It will go till infinity. Okay, so this will be equals to 4 IDC. IDC is 15 ampere. So so they are asking me the fundamental component, right? The RMS value of the sorry, not the RMS, the amplitude. So they are asking me the amplitude itself. So the amplitude of the fundamental component would be 4 into IDC upon pi, where n is equals to 1. That is the amplitude, right? Amplitude of this sinusoid. So amplitude basically means the coefficient of the sinusoid. So yeah, so IDC is 15. So 4 into 15 by pi, this will come out to be 19.09. 19.09. That's all. That is the answer. I think previously okay, the RS, hold on, they're asking me the amplitude of the fundamental component. If I'm doing, okay, sorry, I missed something. Yeah. So, okay, there is one term as well. Okay, this thing you have to unfortunately remember. This you have to remember actually. So, previously, right, this Fourier series expansion, whatever I discussed here, I think somewhere I discussed the Fourier series expansion. Yeah, this was for a proper diode rectifier. Okay, whenever there is a firing angle alpha, so this unfortunately you have to remember, and this is mentioned in the revision X notes as well, right? So you will have to add an extra alpha by 2, n alpha by 2. So your Fourier series, just give me 1 second. Fourier series expansion, this will be there. Along with this, there will be an additional term known as cos of n alpha by 2. This will be there actually. Okay, this term also will be there. So actually your amplitude will have cos of n alpha by 2 as well, cos of alpha by 2, because n is 1 and alpha in our case is 45. So this will be this multiplied into cos of 22.5 degrees. So 22.5. So 17. 17.65 amperes. So this will be the amplitude and this will be the answer. So this part I missed, but this again is a very important thing that has been mentioned in the revision X notes. So I hope you are going through it. So make sure you go through it, right? Yeah. So let's start this next question. So next question is a single phase rectifier consisting of 3 thyristors T1, T2, T3 and D1 is a diode. Feeds a constant power with which load which takes a 10 ampere of current, right? Constant load which takes a current of 10 amperes. So T1 and T3 are fired at alpha equals to 60. T2 is fired at alpha equals to 240. That is after 180, which is a normal operation only. It's because this is fired in the first half cycle. This should be fired in the second half cycle. Okay. The reference alpha is positive for the zero crossing Vin. The reference for alpha is positive for zero crossing of Vin. Okay. Basically, this means that whenever there is zero crossing, after the zero crossing, we fire the alpha. So reference is here 0 degree, and after this we fire the T1, T3. The average voltage VO across the load will be. Now this question is a bit interesting. So the load current is always constant. So I fire my thyristors T1 and T3 at alpha. Before this, what will happen? This T1 and T3 are off, so no chance for the current to flow from here. So diode, like this is taking constant load current. So diode must be turned on before this. So diode is on before this, right? And of course T3 is off. So someone will force this T2 to be on. Who will force this? Load. Load will have some inductance that will force this T2 to be on. So this will be on. What will happen? The flow of current will be something like this. So not something like this. Flow of current will be something like this. It will go start from here, start from here, start from here. Remember, there is no freewheeling diode here. No freewheeling diode. So source will still deliver some current, right, before this. So what is the voltage at this point of time? If you remember, if you see, this is my positive reference, right? So if I write the KVL VO, if I write simple KVL, right? So let me start from here, minus VO. Now this point is negative, right? This point is negative, minus VS equal to 0, because I am coming back to the same point, right? Hold on, let me check. Hold on. So this diode is on. So okay, let me go along with the direction of the current. So I start from this point. This is plus VO. Then I will start from here. Plus VS equal to 0, right? That is my KVL. So plus VO plus VS equals to 0. So basically my VO from 0 to alpha, right? 0 to alpha is equals to minus VS. So if my VS is this, right? My VO VO, it will be negative of VS, right? Negative. Then as soon as it will be triggered, it will be equals to Vs. As soon as T1 and T3 will be triggered, now if I apply the KVL, now this diode will be turned off, diode and thyristor. What will happen if I apply the KVL now? Let me start from this point. T1 is on, so plus VO, T3 is on, minus Vs, because this point is positive, this will be negative, equal to 0. So plus VO minus Vs equal to 0. So this will be VO will be equals to Vs. VO will be equals to Vs in this case. Plus VO minus Vs will be equals to 0. That's why. So this will be continuing till the next cycle, right? Till next time pi plus alpha comes. Correct? Next time this will be pi plus alpha. But again this cycle will be repeated basically. Correct? Because every thyristor will be conducting for pi, because current has to be constant on the load side. So we can easily compute the, so they want me to compute the average load voltage, that will be equals to 1 by pi integration VO of t d omega t from 0 to pi, right? I can compute that. So should I compute from 0 to pi? That will be a bit tedious because this is not proper sinusoid, right? But if I see from alpha to pi plus alpha, it follows the same curve. This is a sinusoidal curve, right? But here from 0 to alpha, it is minus of Vs, and from alpha to pi, it is plus of Vs. So that will be a bit tedious. I have to change the definitions, although you will get the same answer. But for our convenience, we'll choose from alpha to pi plus alpha. In this, the definition of VO of t is same, constant. That is Vs. So this will be 1 by pi this will be Vm sine omega naught t d omega t sin omega t d omega t alpha to pi plus alpha, right? So this will be basically, if I integrate this will be Vm by pi cos of alpha minus cos of pi plus alpha. This will be equals to Vm is 100 by pi cos alpha. What is alpha? Alpha is 60. Alpha is 60. So cos 60 is half minus cos of pi plus alpha, that is basically 240. What is cos of 240? It is minus of half. So this will become minus of, right? So your answer would be simply 100 by pi. Okay. So what is 100 by pi? I will have to compute this if I'm doing everything correctly here. So voltage is 100 pi t, load current is constant, yes, everything is okay. So okay, yes, I'm just thinking one thing. Now this part I think we have done this wrong way. So what happens at omega t equals to pi? That is what I was thinking. Like I just got this in my mind. I'm thinking also. I did not do the analysis here. So as soon as the VO or the voltage, source voltage, goes negative, right? What will happen? Actually, one of the thyristors, this will turn off. Okay. As soon as this voltage goes negative, one of the thyristors will turn off. But still, load is taking some current. Load is taking some current. There will be some inductance in the load that will make the current continuous. Right? One of the thyristors will be turned on, turned off. So after this, what will happen is that so I'm triggering my T3. Okay, yeah, what will happen? So this, if you see in the full course that we have discussed. So what happens? So at omega t equals to pi, what happens? This voltage goes to negative. Negative. We are in the negative half cycle. So what will happen is I have not triggered the T2 yet, right? So T2 will not be on. T2 will not be turned on. Okay. And T1 and T3 are still on. What is the problem here? And current is in this direction. Do you understand what is the problem? T1 and T3 are on, voltage direction has changed. So now the power, right, is flowing from load to source. This I have taught in my full course. Let's say if this load will have some inductance, right? Power will flow from load to source. Power will start to flow from load to source because this source voltage has turned negative. Okay, and current is still in the same direction, right? If T1 and T3 are on, current direction will be this only, right? Current direction will be this only. So current is entering the positive terminal of the source. So source is absorbing power. Just before omega t equals to pi, source was delivering power. So at omega t equals to pi, it is just beyond omega t equals to pi, it is absorbing power. This is a problem. So load will de-energize. So load always wants to keep its own power. You always want to keep your own money. You don't want to spend your money, right? So load also always wants to keep the power. So what the load will think is it's very difficult. If I keep the T1 on, that is consuming power from my load. What if I generate enough voltage to keep the D1 on, and T3 is always on, T3 is already on, it will be on. So if the D1 is turned on, what will happen? T1 will be automatically turned off, because if you apply the KVL across the T1, it will be in the reverse bias. You can do it. So all this I have taught in my full course, so I'm not explaining over here. Okay, there are many concepts, so that's why you have to study the power electronics first, then you can come back. Now this will be reverse bias. So the load will do what? It will turn on the D1. As soon as it turns on the D1, the VO voltage is 0. Now load does not have to deliver the power to source anymore. Only it has to keep the D1 on. It is happy. Load does not have to spend power. You do not have to spend money. Which path you will choose? Spending money or not spending money? You will obviously keep that money. You will eat some pizza burger by yourself, and you will not spend that money, right, to someone else, like buy your courses. Okay, of course, you will not buy your courses, you will eat pizza burgers, right? So that's the thing actually. That is what is happening over here. So that's the point. So it will keep the D1 and T3 on. And if D1 and T3 are on, that means what is the voltage? VO, it is 0, right? It is short circuited, it is 0. So this is a very interesting point that will happen from pi to pi plus alpha. This point I actually forgot to mention. I'm sorry, extremely sorry, I missed out this point. Otherwise this will be just a simple bridge rectifier only, right? Yeah, that's the point that you have to catch here. I missed this point. So actually you will integrate from 0 to pi only, because beyond pi to pi plus alpha it is 0, right? So the area will be 0. So actually this will come out to be cos alpha minus of, okay, then what happens at pi plus alpha? So at pi plus alpha, my T1 and T2 will be triggered, right? T1 and T2 will be triggered. Now if T1 and T1 and T2, sorry, T2 will be triggered. If T2 is triggered, right, then this T2 will naturally commute T3. So if I apply the KVL, as soon as the T2 will be triggered, what will happen? You will see that voltage across T3 is negative, so it will go reverse bias. So the current will now flow in this direction. So current will flow like this, right? I can show how the current will flow. So if you see, current is leaving the positive terminal of the source. Now source is delivering to load likes it. You are getting money, you are liking it, right? You enjoy it. So then obviously it will not have any problems. So in this junction, my voltage here is negative, and my VO is minus Vs, right? So whenever T2 and D1 are on, VO is minus Vs. So the voltage will be somewhat like this actually. Okay, this is interesting. Voltage will be somewhat like this. So it is negative, it will be positive, and it will go like this. Until what point? It will go till the point 2 pi. Because again after 2 pi, okay, actually I was wrong here, right? I was wrong here. Initially this voltage will be negative. Oh, yeah, this will be actually negative only. Why? Because this time, right, I don't have a diode anymore. I have this thyristors only. So this T2, so now what is happening? So what is the current scenario? T2 and D1 are on. Okay, don't worry, I will explain. I will repeat again. Don't worry, I will repeat again this part because you might feel confusing what is happening. So after 2 pi, right, just before 2 pi, T2 and D1 are on. T2 and D1 are on. Now as T2 and D1 are on, as soon as the voltage will go after 2 pi, the polarity will change. Again you will say, sir, we don't like it. It does not like to deliver, the load does not like to deliver power. Now you don't have that option. What option? To turn on T1 and T3. Why? Because T1 and T3 will never turn on until they are triggered, right? That was the beauty of diode. Diode, you don't need to trigger. Only the voltage across the diode will decide whether the diode is on or off. But for thyristor, you need to trigger it. So although the load wants this T3 and T1 to turn on, but it will not be able to turn it on because they are not triggered. So still T2 and D1 will be still on. And this time the load unfortunately has to deliver power to the source. So when T2 and D1 are on, the voltage will be minus of Vs. So if voltage is minus of Vs, still it will follow the same graph. Okay. If voltage is minus of Vs, so minus of Vs meaning this is positive, this will be negative, and suddenly as soon as they will be triggered, again they will turn on and it will start from here somewhere. Okay. So that's a graph basically. So this is not, there is no, there is a cycle of 2 pi. It is not repeating after every pi. I was wrong here. So okay, let me I will come to the average voltage part. Let me first explain you what is actually happening. I was super wrong here. So that will be best case scenario if I explain you actually what is happening. Okay, that's the best case scenario. Let me do this question again. Okay, so what is happening over here? Hold on a second. So load current is constant. Okay. Now let us start from omega t equals to alpha. Let us not get to before alpha. I will explain obviously what will happen, but let us start from omega t equals to alpha. The moment alpha comes, right, T1 and T3 are triggered, so these two thyristors will be turned on. So load current is constant. So what will happen? They will automatically commutate the previous thyristors, and your current will flow like this. Hold on a second. T1, T3 will be turned on. Current will flow like this, right? Yes. So current will flow like this, correct? So what is my, this is my Vs, this is my VO. Apply the KVL, you will see that your Vs is equals to VO. So omega t equals to alpha to omega t equals to pi, your your VO will be equals to plus Vs, no problems. Now what will happen just after pi, or just at pi to pi plus alpha? So from pi to pi plus alpha, omega t equals to pi to pi plus alpha, pi to pi plus alpha, what will happen is this voltage will change. So this will be like, although this is my plus minus Vs, but this Vs is negative, so this point will be more positive than the top point, right? This point will be more positive. So that can turn this diode on if you want to turn it on, right? If this T1 is turned off, okay. What the inductor will do, because the current needs to be continuous, again for the same reason that I explained previously, the load does not want to deliver power to the source, because if T1 and T3 are turned on, if T1 and T3 are turned on, then the load has to deliver to the source. It does not like that, so it will turn the D1 on, and it is proved. If the D1 is on, right, then you see this potential is plus this the moment. Okay, let's assume that this D1 is not on. Okay, you assume D1 is not on and T1 is on. At omega t equals to pi plus, what will happen? This point is plus, right? And T1 is still on. You assume T1 is still on. So this is short circuited. So this negative point comes here. So you're applying a positive voltage across the diode D1. So it doesn't matter what the load wants. D1 will anyways turn on. Okay. D1, although like that was an intuitive way to understand that, but anyways you can see the voltage across the diode is positive from anode to cathode. So D1 has to turn on. So as soon as D1 will turn on, it will naturally commutate T1. Why? Because as soon as D1 will turn on, right? So this will be short circuited now. So if this is short circuited, if you see the voltage across T1, this is plus, this is minus, right? So cathode has higher voltage than the anode. So as soon as it will turn on, it will naturally commutate T1. That's all. So T1 will be automatically turned off. So as soon as T1 is turned off, T2 is anyways off, right? We will trigger T2 at 180 plus alpha, that is 240 degrees. So still T2 is off. T2 is still off. And T3 is still on. Okay, because T2 is off, T3 will not be naturally commutated. So what will happen is that obviously load current is constant, so current will flow through this path. How? So load has a source, load has an inductance that will make the current continuous. That's all. So in this region from omega t equals to pi to alpha, the omega t equals to pi plus alpha, the current is constant, the voltage is 0. And trust me, no one will explain like this. No one. You go into any content, any PYQ revision video, they will just directly solve the question. They will not explain you. I am explaining you the concepts. Okay. So omega t will be from pi to pi plus alpha. That's all right. Now, what is happening after pi plus alpha? After pi plus alpha, we are triggering T2. As soon as T2 will be triggered, it will be turned on. As soon as it turns on, you will see the voltage across T3 will be negative, so it will be off. So now T2 and D1 will be turned on. Now there will be normal operation. What is a normal operation? So from omega t equals to pi plus alpha, pi plus alpha to 2 pi, this will follow. What will be followed? VO will be equals to minus of Vs, right? Now from 2 pi plus alpha to 0, or you can assume from now we can come to the first state, right? Omega t equals to 0 to alpha. What will happen to VO? Now from 0 to alpha, what will happen? 0 to alpha at omega t equals to 0, 0, right? Omega t equal to 0. Omega t equals to 0 to alpha, right? Omega t equal to 0 to alpha. Average voltage across the load. So now from 0 to alpha, what will happen is this D1 will be okay, because 0 to alpha, this T2 and T3 will not be turned on, right? Because they will be triggered at alpha. Okay, so they're off and current is constant. So only one possible condition is there. T2 and D1 has to be on. There is no other possibility. T2 and D1 has to be on because current is constant. T1 and T3 are off. They will not be triggered till alpha. So D1 and T2 has to be on. So whenever T2 and D1 are on, that is just then my VO, you can apply the KVL, will be minus of Vs. Okay. So unfortunately, this will be a bit lengthy, and that's fine. It's good. These questions come. So VO average will be equals to, now this will follow the how will the graph look? So initially it will be minus of Vs, right? Then at alpha it will be plus Vs, and then again it will go till pi, then it will be 0 for a certain time, then again it will be minus of Vs, that will be this, and then again it will be this. Okay, so the graph, right, is periodic with a period of 2 pi, not pi. So if I solve this, we can solve this in two parts. So we can, so this will be 0 to 2 pi v of t dt d omega t vu. So this will be equals to, this will be Vm. Now Vm is just a constant number. This will be interesting. So I have to integrate sine. So from 0 to alpha, right? It is minus of Vs. So this will be minus sine omega t from 0 to alpha. Then from alpha to pi, it is plus sine omega t, right? So don't forget there is d omega t here. From pi to pi plus alpha, it is 0. So from pi plus alpha to 2 pi, it is again minus sine omega, right? This is negative because from here to here actually sine is negative, right? We are making it positive. So it is minus sine omega t dt. Now we can solve it. So what is your Vm? Vm I think is 100. Vm is 200, right? So 100 by 2 pi. This will be, so this is negative. So this is positive cos omega t only, cos omega t. So cos alpha minus cos 0, that is 1. It is fine. So yeah, yes, that is fine. Because integration side is minus cos minus will go there. Yeah, cos alpha minus 1 plus this will be uh, cos alpha plus 1. Okay, and this will be again minus, so this will be cos of 2 alpha. So cos of 2 pi, cos of 2 pi is basically 1 only, right? Yeah, cos of 2 pi is 1, cos 360 is 1, and minus of cos of pi plus alpha. Now cos of pi plus alpha will be minus pi, right? Because we know our, let's say if cos is here, sine is here, if I shift my cos, if I add plus minus pi, simply this is minus of cos, right? That's all. Okay, so that's how we remember it. So this, right, will be 50 by pi, 1 will be cancelled, 1 plus 3 cos alpha. Okay, alpha is I think 45. Is it what it is? It is 60. Alpha is 60. Okay, cos 60 is simply half. So it is actually 3 by 2. So 2.5, right? So it is 2.5 into 50 by pi, which is 39.789. 39.789 volt. This will be your answer for the question. Pretty good question. Like you can learn a lot of stuff from here. Okay, let's solve the next question. So a single phase half controlled bridge converter. Now what is this half controlled bridge converter? Half controlled, sometimes it is also called as semi controlled, right? This unfortunately again you have to remember. So it is a bridge rectifier with a bit of modification. What is the modification? So the modification is, if I copy this, right, just give me 1 second, let me take it here. It is a bridge rectifier with a freewheeling diode. That's all. That is the only thing that is different. So there will be a okay. So this is a freewheeling diode called as FD. Now rest things are same, so this will be a thyristor only, because like we're talking about a standard circuit. So in standard circuit everything is thyristor. Okay, so this will be T4. Now what will happen with a freewheeling diode, right? So what are they asking? They're asking supplies an inductive load with ripple free load current. So basically the load current is constant. The triggered angle is at alpha equal to 60. We're triggering it at alpha equal to 60. The ratio of the RMS value of the fundamental component of the input, basically the source. So IS1 RMS, IS1 RMS upon the RMS value of the total input current of the bridge. So input means total source current, right? So IS RMS. That is what they are asking. IS RMS, right? How do I compute this? So this will be basically so if you remember the Fourier series expansion, which we have discussed multiple times, so what will be the graph? Basically waveform. I will not explain everything here because that will be too much. So basically from 0 to alpha, right, this freewheeling diode will conduct. Okay, from alpha to pi, T1 and T2, T3 will conduct, because at alpha both T1 and T3 are triggered. Before that they are not triggered. Then again from pi to pi plus alpha, T4 or T2 are not triggered, and because what will happen, this potential will be low, right? So these are on at omega t equals to pi, these are on T1 and T3. So what will happen, this potential has been negative, so this potential is negative, this potential is positive, because these are shorted. So what will happen, that will turn this freewheeling diode on, and if the freewheeling diode is turned on, it will naturally commute T1 and T3. Okay, this kind of concept I have discussed in a previous question, and if you're not able to understand this, then you have to go and revise and watch any full course. Okay, because this is not the purpose of this video. The purpose is practicing of questions. Now this will turn it off. So basically the current from the input is 0, but current through the freewheeling diode is non-zero. And again at pi plus alpha, T2 and T4 will be triggered. So again that will naturally commute the freewheeling diode. Hence again the current will flow in the opposite direction. So the graph will be somewhat like this. From 0 to alpha it will be 0 for the source current. Then again from pi till pi it will be IO. Then again from pi to pi plus alpha it will be 0, and again it will go negative, and again it will go positive. So this will be 2 pi, and this will be minus IO. Plus I omega t. Okay, so yeah, now that I'm thinking that okay, maybe I wrote something wrong. So the gate exam, right, this for this question they gave this as the range. Okay, this was the solution everyone gave, but I think the solution that everyone gave is wrong, because this is not the I also don't remember the Fourier series expansion. I also have it written in the notes, and then I see from it, and once in a while it does stay in my mind, but most of the time it does not. But what currently is clicking to me, this Fourier series is wrong. So this Fourier series expansion, right, is not for this particular square wave, it is for this square wave. Okay, where the phase shift will not be n alpha, it will be n alpha divided by 2. Okay, this will be the phase shift. I actually made a mistake. I think in the revision X notes it is properly mentioned. Okay, so just a mistake on my behalf. Here this will be right. This Fourier cos n alpha will not be there actually. So I will just cross that, this will not be there. Okay, only this part will be there. This will be there. This will be there. So actually this will be not there. Cos alpha by 2 will not be there. So although in the answer sheet, right, they have given their range to be 17.3 to 90, 17.3 to 18, but I believe that here what should happen is the answer should be only 4 IDC by pi, that is 4 into 15 by pi, that is equals to 60 divided by pi. So I believe this will be 19.09 ampere. This will be the answer. That is what I believe. Although in the answer key, I just check now, they've given this as the answer, but I believe this is not the answer. This is the answer. So just be careful. I feel a small minor mistake has been made from their end. That is what I believe. So for this, the Fourier series expansion is this. Now they are asking me what is the IS1 RMS. IS1 RMS will be this divided by root 2, right, when n is equals to 1. So 60 divided by pi, basically that is equals to 19 point, sorry, not 60, what am I doing here, what is the IDC, I don't know. So it is I naught only, right? This I naught, they have not told me. So I want the RMS value. This will be 4 into I naught upon pi divided by root 2. Okay, this is the IS1 RMS. What about the IS2 RMS? So IS2 sorry, IS RMS. So IS RMS is pretty easy to calculate. It is just the, so it is just the RMS of this particular thing, right? So I hope you know how to calculate the RMS. You have studied signals. So because if I square it, right, this will be repeated. This thing will be repeated. That's all. So negative, positive does not matter. So I can only consider this period. That is period of pi. So from 0 to pi, it is IO from alpha to pi. So basically, I will not explain you, but I hope you know. First you compute the energy of the signal, then you take the under root. Okay, that is how we learn in signal analysis system, and this also I have covered in my full course. So this will be basically pi minus alpha divided by pi. Okay, that will be the RMS value here. Pi minus alpha divided by pi into obviously IO. Okay, so yeah, that is the RMS value over here. So the ratio would be IS1 RMS divided by IS RMS. This will be 4 IO or 2 root 2 IO, right, by pi into IO pi minus alpha divided by pi. So this will be pi under root pi. So this under root pi will be here. So what will happen? Under root 2. This will be under root pi into pi minus alpha. So pi alpha is basically 60 degrees. Pi by 3. So yeah, so this will be actually pi can come outside. So this will be 2 root 2 upon pi, and this is 1 minus pi by 3. That is 1 into 2 by 3. So under root 2 only, and under root 3 is also here actually. So under 2 will be cancelled. This will be 2 under root 3 by pi. So let me solve for this. What is 2 under root 3 actually? 2 into under root 3 by pi. So it comes out to be 1.10. Okay, I'm just quickly checking whether I've put all the values correctly here. So pi minus alpha, just checking. How can it come? It cannot come more than 1, right? That is not possible. It cannot be more than 1. Pi this into pi, there will be a, this pi can come outside. Pi into pi 1, that is under root 3. Under root 2 was there, 2 has been cancelled. How is it coming out in more than 1? Because IS1 RMS will be less, right? It cannot be more. 2 pi by 3. 3 is coming there, and root 2 is cancelling out. 2 is all still here. I'm missing something. That is what I'm thinking. What am I missing? 202. Oh, sorry. I'm missing this, right? We're missing this. I'm extremely sorry. Extremely sorry. So we will obviously have to increase this. That was the reason why I got puzzled by the previous question. So cos n alpha by 2, that is cos of n is 1. So it is 60 by 2. That is cos 30. Cos 30 is root 3 by 2 actually. So this will be root 3 by 2. Okay. So into root 3 by 2 into root 3 by 2. So root 3 will be 3, 2 will be cancelled. So this will be 3 by pi. Okay. So what is 3 by pi? It is basically 0.955. That's all. So 0.955 is your answer for the question. Okay. So 0.955 is your answer for the question. Let's solve the next question. A single phase fully controlled thyristor is used for regenerative braking. Do you understand what does regenerative braking means? Basically, my converter operates full bridge converter, right? This is my quadrant 1, quadrant 2, quadrant 3 and quadrant 4. This is my voltage, this is my current, right? So when the uh, load is absorbing power, right, that means we're lying in the quadrant 1. Both voltage and current are positive. This is my load, okay, and the current is positive, so it will enter the current, and this is my voltage. So both voltage and current are positive, that means current is entering the positive terminal, that means it is absorbing, it is working as a load. But when the load starts delivering, when will it happen? When the current direction changes. So if I'm lying in the quadrant 4, then it will behave as a generator. So it is called as regenerative braking. This operation is called as regenerative braking. Or sometimes what we do, we replace the uh, voltage terminals. If I replace the voltage terminals suddenly, right, I will be lying here, right? Not here, sorry, I will be lying here. This quadrant is also called as the regenerative braking quadrant. So either this quadrant, quadrant 2 or quadrant 4, these are called as a generation quadrant, where the load delivers to the source. Okay. So these are the specs. I will come to the specs later. Uh, the armature of the DC motor is fed from a fully controlled bridge and field current is kept constant. Okay, field current is kept constant. Assume that the motor is running at 600 RPM. The armature terminals are suitably replaced. So here what they're doing, they are replacing the armature terminals. So if they replace the armature terminals, so this is my output of the converter, right? That is plus minus VO. Previously it was connected like this, plus was connected to plus, minus was connected to minus. But now what they are doing, they are interchanging. Plus is connected to minus, minus is connected to plus. That's why they are interchanging. So if they're interchanging, what will happen? The voltage will reverse its terminals. Current will not instantaneously change because it is an inductive load. So this, I will be lying in this region, and this region is called as regenerative braking, where the load is delivering power to the source. So if it is delivering power to the source, of course it has some energy, kinetic energy, that will reduce, because whatever energy it has stored, that it will use to deliver the power or energy. If the armature current of the motor is to be maintained at the rated value, basically whatever is the value, that armature current will be remaining constant. Uh, the triggering angle alpha of the conductor in degrees should be, okay. So basically, what is the rated armature current? That is 10 ampere, right? Now remember what they are telling us here. They are swapping the armature terminals. So this is the load. Actually, here bit of correction is there. So I'm not actually swapping the load terminals. So what do they mean by armature terminals? For that, let me draw the DC machine first. So this is my rectifier output, VO average, right? I will get some average voltage right from the DC rectifier output. That is there. Then I have the armature. Then I have the armature resistance. Then I have the armature actually, right? Okay. Then I have the armature. And armature, in normal operation, it will provide some EB, amount of back EMF. But what we are doing, right, we are actually swapping the terminals. So what we are doing, is this part is not connected here, this part is connected here, and this part is connected, okay, so not here, whatever, not here, and hold on, Okay, this, sorry, what am I doing? So this will be, okay, just let me clear this up. This will be connected here, and here I have RA. So this will be connected here. That's all. So basically, this is plus. This will still be there, right? This, obviously the voltage will not change suddenly. What will happen is, what will be the VO now? So VO would be uh, RA. So this is the current, right? DC current, IO, that will not change suddenly. IO into RA and minus EB. It will not be plus. It will be minus. I hope you can do the KVL and you can understand, right? And it will be minus because we know when the converter operates in generation mode, right, or braking mode, regenerative braking mode, or it is also called as inverting mode, then the alpha will be greater than 90. Then only the average voltage will be less than 0. All this you have, I think you have learned. So we know at rated speed, this is the voltage, right? So EB, rated armature voltage, right? EB rated, we know it is proportional to phi upon phi ZNP. EB is equal to phi ZNP upon 60A, right? So it is proportional to flux and the speed, basically, for K phi into N, right? So flux is constant in our case, correct? Flux is constant in our case. So what is varying? The thing that is varying is speed, right? So because at rated speed I get the rated voltage, but currently my armature is not operating at rated speed, it is operating at 600 rpm, which is half the rated speed. So the voltage also will be halved because other thing is constant. This you can simply do a simple ratio, EV1 by V2 equals to N1 by N2. N1 is the speed of the first one, that is 1200, then 1200 by 600, right? And rated voltage is 210. So your EV2 will come out to be 105. So from this I will get the value for my average voltage. So remember, armature is operating at rated current, that is what they have mentioned me. If you see what is mentioned, armature current has to be maintained in the rated value. So IO will be IO rated, that is 10 ampere. RA is given to me, RA is 1 ohm, right? So this will be 10 into 1 ohm minus EB. EB in this particular speed is 105. So your average voltage or output voltage of the converter comes out to be 95 minus 95, right? It is negative. And we know for a full bridge converter, right, you can obviously derive it. The input voltage is sinusoidal 240. So 240 at 50 hertz, right? So remember, this is RMS value, right? So we know VO average of a converter, full bridge converter, is Vm by pi cos alpha, 2 Vm by pi cos alpha. This you can derive it. How can you derive it? Simply, what is your output voltage of a converter? Output voltage expression for a converter is this, right? Without any FD freewheeling doubt and such. They have not mentioned any freewheeling doubt, so I will assume it to be normal full bridge inverter. So in this case, right, in this case basically this will be 2 into, so VM is, RMS is 240, so 240 root 2 by pi cos alpha, and our Faraday angle is not provided, that is what I have to find out. That is will be equals to negative, right, minus 95. Okay, so let me solve this. So 95 into pi divided by 2 into 240 into root 2. So that is 0.95 negative. So if I do cos inverse, that is 116 degrees. Okay, so this will be 106. So alpha will be coming out to be 116 degrees. Now, have they asked in degrees or they have asked in radians? They have asked in degrees. So it will be they have asked in degrees, right? So it will be 116.08 degrees. This will be your answer for the question. Okay. Yeah, let's solve the next question. So this is the next question where we have a single phase uh, triac, okay, AC controller. So single phase triac AC controller is nothing but somewhat like this, right? So we have simply a triac connected, okay. uh, it is essentially a back to back SCR. That's all. That is all about my triac, right? uh, this is a single device. I also have forgotten exactly how to draw the terminals, but I think mostly this is how we draw the terminals. I don't remember basically. Yeah, and here I have the input and here I have the load, right? So essentially what we do is we just control the AC voltage. What is the average AC voltage, right? Not average AC, sorry, we control like what is the voltage level that we can get to. Okay, now what are they asking us? So it feeds the RL load. So load is RL. The input AC supply is 230 volt 50 Hz. The values of R and L are this. The minimum triggering angle to obtain controllable output. So I've already told you, right? I will get a controllable output, triggering output alpha, when this alpha will be greater than my phi. Otherwise, if I give my alpha less than phi, then the output will not be controllable. The load will always keep the triacs on. Okay, this is something that you have to remember. So what is phi? Phi will be tan inverse omega naught L upon R, basically the imaginary component, reactive component upon the real component, right? So it will be tan inverse omega naught L by R. Okay, so this will be tan inverse omega naught L by R. So omega naught is what? It is 2 pi f, right? So 2 tan inverse of 2 into pi into 50 into f is there already into L. L is 18.37 millihenry, correct? Divide by R. What is R? R is 10. Let me solve this. Let me calculate the alpha minimum. That will be my alpha minimum basically. Okay, this will be my answer, right? This is the minimum amount of ID angle that I have to provide for the AC this to trigger, right? This things to trigger for the voltage regulator to control the voltage. This again I'm stressing that you will have to unfortunately remember this thing. There is no other way out in this. Okay, unfortunately you will have to remember this 10 inverse, which comes out to be, so your phi comes out to be 30 degrees. So this is the minimum value of alpha, right? This will be my alpha minimum. If I give a triggering angle less than this, my SCR will never trigger. Okay, so minimum angle that I have to give is 30 degrees. That is the minimum angle. Okay, so 30 will be your answer for the question. Let's solve the next one. Simply you have to find out the input power factor. I guess I don't need to explain this much. Simply what you have to find out is what is the formula for input power factors. Again, like they repeat the same question over and over again. Input power factor is the total active power consumed, active power of the supply divided by the total apparent power. Apparent power is nothing but the product of the RMS voltage into RMS current. So what is active power? Active power will only contain the like frequency components, same frequency components. So it will be fundamental of the voltage, fundamental component of the current, right? So if I had a sine of 3 omega naught t, then I would have multiplied these two things, okay? Because here I have 3 omega. So only the same frequency terms will contribute to power. This I have already taught, and I hope you know this. This we have learned in signals, this we have learned in network theory, this we have learned in power system. If you have, sorry, not power system, if you have studied power electronics, there also this will be taught. So this will be 10 by root 2, and the angle, cos of the angle between these two components, that is pi by 3. So cos of, sorry, not pi by 3, pi by 6 divided by the apparent power. Now apparent power will contain everything. So RMS value of this, that is 300 by root 2 into RMS value of this, right? That is 10 by root 2 plus so RMS of this whole thing. So RMS of this, right, will be 10 by root 2 whole square plus 2 by root 2 whole square plus 1 by root 2 whole square. So this thing will be whole under root. So if I solve for this, this is 100 by 2, that is 50 plus 4 by 2, that is 2 plus 1 by 2, that is 0.5 whole under root, that is 7 point. So your IRMS is 7.245 amperes. Okay, 7.245 amperes. So your IRMS is 7.245 amperes. Anyways, this thing will be cancelled, right? This thing will be cancelled. Ultimately, I have to consider this part. So this will be equals to this into 10 divided by root 2 into cos of 30. Cos of 30 is root 3 by 2. So it comes out to be 0.845. Okay, 0.845. And your options are also very close. So you have to be very, very careful, right? Your input power factor is 0.845. So option A is correct. Options are also very, very close. So you have to be very careful. Other options are very, very close, right? Let's solve the next question. So in this question, an ideal sinusoid voltage source Vt is given, and ideal sinusoid, voltage source is given. It feeds an ideal inductor. The SCR firing angle is alpha equal to 0. If L is 100, then the peak of the inductor current would be. So this I have derived in my full course. What will happen if the SCR, whenever the SCR is triggered, right? Inductor will turn on. Slowly, the inductor will energize. For the positive half cycle, inductor will completely energize, and whatever energy it has got, because there is no resistive component, all of the energy will be delivered to the source in the negative half cycle. So what will happen is the voltage across the inductor will look something like this, because your supply will always be on. So from 0 to alpha, what will happen? The source will keep this SCR on. From alpha to what I'm taking, from alpha to pi, the source will keep this SCR on. From pi plus alpha to 2 pi, the inductor will keep the SCR on. If you don't understand these things, you have to go and watch the full course. There we have explained all these things, right? In our case, our alpha is 0. So technically it becomes from 0 to pi, the source will keep the SCR on. From pi to 2 pi, the inductor will keep the SCR on. So basically for the first half, the inductor will energize, and whatever energy it has stored, all of it will be gone in the second half, because there is no resistive component. So the timing will be equal exactly. So this will be the load voltage here. This will be the load voltage, and what will happen to the current? So current, right, will keep on increasing, because we know VL equals to L DIL by dt, correct? So whenever the voltage is positive, this DIL by dt is positive, that means current is increasing. So till pi, the current will always increase. Okay, and then from pi to 2 pi, the current will reduce, because voltage is negative, so current will reduce, and it will be 0, touching 0 at 2 pi, and then again this cycle will repeat. Okay, they are asking me what is this current. It is very easy to calculate. I know the voltage, right? I can simply integrate to get the current. So your IL will be 1 by L integration of VL of t dt. Now your VL is nothing but the supply voltage, because SCR is always on. So it will be 1 by L Vm sine omega t dt. Okay, so Vm by omega L into cos omega t into so I can integrate from 0 to 2 pi. So not 0 to 2 pi, sorry, 0 to pi, because what I have to do actually, so what happens, this is DIL, right? So DIL, right, I can integrate from 0 to IL max. Or okay, let me do one thing. Let me compute the expression for IL. Let me just simply, let us not put limits over here. Let us compute the expression for IL, right? So yeah, let us compute the expression for IL, or no, let me do it. Let me compute. Okay, we can compute the expression for IL. So we're starting from t equal to 0 to t equal to t, right? And we're starting from IL equals to 0, because at t equal to 0, the current was 0, and I'm going to IL of t, right? So t equal to 0 to t equal to t. So this will be Vm by omega L. Hold on a second, there will be a negative sign, right? There will be a negative sign because I'm integrating, there will be a negative sign. I'm integrating sign. So this will be 1 minus cos of omega t, correct? This is my IL. There will be a negative sign because I'm integrating sign. So if you put t equal to 0, you get current is 0. That makes sense because t equal to 0, nothing is there, right? Current will be 0. And at t equals to pi, if you put t equals to pi here, the current will be maximum. So this equation does make sense. What is the maximum value of the current? It is 2 Vm upon omega L. So Vm is this 230 root 2. So 2 into 230 root 2 into 230 divided by omega, that is 2 pi into 50 into L. L is 100 millihenry. Okay. So this will be 230 into 2 into root 2, sorry for the noise, this divided by 2 into pi into 50 into 100 into 0.001. So this comes out to 20.7 amperes, right? That is the peak value of the current that is present in option A. So option A will be the correct answer for this question. Okay, let's solve the next question. This is the last question, I guess. So we have a 3-phase rectifier here. So they have already given me the expression for voltage. Okay, for a 3-phase rectifier, they have already given me the expression of voltage. They are very smart. Okay, where alpha is the firing angle, if the power dissipated is 64 watts, then the closest value of alpha would be. So power dissipated is 64 watts, right? So if they're talking about the power dissipation, let me compute the. So nowhere the frequency is mentioned, correct? Of the voltage is mentioned, right? Frequency of the voltage. So I'll assume omega to be very high, very very high. Why? Because I want very fast switching, so that what happens, the inductor is replaced with short circuit. Sorry, I'm talking. Yes. Sorry, hold on a second. So what I want my time. Sorry, I want my omega to be low. So I want my time period to be very very high. If time period is very very high, right? So basically this time period or t by 2 must be very very greater than the tau. So basically this will always settle. That's the point. T by 2, if t by 2 is very very greater than tau, right? Tau, the time constant of the load circuit, then the circuit will always settle. So basically I can assume the load current to be constant. So because nothing about t by time period of the supply is mentioned, so I will assume that it is much much greater than the time constant of the load. That means I can assume that the load current is constant. So that is the point. The point is you have to assume the load current is constant, otherwise you will not be able to solve this question. If you assume the load current to be constant, this inductor can be replaced with a short circuit. Okay, because if load current is constant, the voltage is 0. So essentially your circuit will be this. Now here you have to measure the power dissipated. What is the power dissipated? And here I will have the VO average, right? Whatever is the voltage VO average, that I will have. This will be some value VO, correct? It is a DC voltage. Now what I will do is I already know the power dissipated in the resistor is 64 watts, right? What will be that value? Power dissipated in the resistor, so that will be equals to IO. Because it is constant current, it won't matter if I write IO average, IO RMS, all these things won't matter basically, right? So I can write IO square into R, that is 1, that is equals to 64. Okay, IO square into R, that is equals to 64, right? So your IO equals to 8 ampere, right? IO is equals to 8 ampere. So I got my IO value, that is equals to 8 ampere. What about my VO? What will be VO? VO will be equals to if I simply apply KVL, it will be IO into R, IO into R plus 500, correct? So your VO would be equals to 500 and 8 volt. That is my VO voltage, right? And this is equals to the formula that is given. So we don't have to derive anything. They have already given me the formula. So this is actually a good question, because it is very tedious to derive the formula for a 3-phase rectifier. It becomes very hectic. So it is already given 400 1 plus cos alpha by 3. So from here you will be able to find out the value of alpha, right? So 500 watt divided by 400 minus 1 into 3 cos inverse. So alpha comes out to be 35.9 degrees. That's all. Alpha will come out to be 35.9 degrees. This will be the answer of this question, and this will be the end for rectifiers. Now we will move on to choppers. Let's begin with chopper, right? So this is the first question. The figure shows two buck converters connected in parallel. Okay, the common input DC voltage for the converters has a value of 100 volts. Okay, the common input DC voltage for the converter has a value of 100 volt. So this is the common input voltage. The converter have inductors of identical value. So these inductors are of identical values. The load resistance is 1 ohm in parallel with a C. The capacitor voltage has negligible ripple. That means the load voltage is almost constant. That means the current right through the resistor is also almost constant. Both converters operate in continuous conduction mode. Basically, the inductor current will never go zero. That is what we mean by continuous conduction mode. So inductor current will always be continuous. It will not go zero. Okay. So they will basically turn on this diode. Now what are the asking? The circuit operates in steady state, assuming the converters share the load equally. So the converters share the load equally. That basically means that whatever the power that converter 1 will deliver, the same power converter 2 also will deliver. So it will be P by 2, P by 2 if the overall power is P naught. So what is the power at the load side, that we will discuss. Now what are they asking? They are asking me the average value of the current IS1. So here what do we know? We know that the load voltage is constant because it has no ripples, right? So let us assume that the load voltage is something VO, that is a constant value, right? So let us assume, let us take the first case. Okay, this was previously I was doing something else. So let us assume that if I consider the previous case, right, when the switch S1 is on. So when the switch S1 is on, then this will be the circuit, right? There I will have the inductor, switch S1 is on, this is L, this is C, this is R, and here is my voltage VO, and this is my voltage VL, and this is my 100 volt, right? So what is happening is, what is the voltage across the inductor from 0 to 0.5, because this voltage is fixed, right? VO is fixed because it is some ripple free voltage. This voltage is fixed, so the voltage across the inductor also must be fixed. What is it? It is 100 minus VO, right? So this voltage, let us assume that VO is smaller than 100, so it will be something positive. 100 minus VO, just give me 1 second. 100 minus VO. Okay, now what will happen when this switch will be opened? Now when the switch will be opened, right, at t equals to, so this is still the point, t equals to 0.5 milliseconds, right? Now when the switch will be opened, the other converter will be turned on. So what will happen now? Other converter will be turned on. This converter, if I draw the circuit properly, and this will be here, this will be turned on. There I will have inductor, this will go on to the top side here, and this will connect to the through a diode, this will connect to here, correct? So now again the same case. So what is the voltage across the, this is the inverter 1, right? So I'm plotting the inverter, sorry, not inverter, sorry, converter 1. What is the voltage across the chopper 1, right? Converter 1. Now what is the voltage? Remember, inductor has to operate in continuous conduction mode. It has told us, right? Both conductors operate in continuous conduction mode. If both converters operate in continuous converter mode, then this inductor must have some current. From where that current will flow? So here, right, no current can flow. This switch is open. Only possible path for the current to flow is from here. So some current will flow that will keep this inverter on. If this current is flowing through the diode, so this diode is on. So essentially, I can replace the diode with a short circuit. Okay, with a short circuit. So interestingly, this side voltage is VO, this is VL1. So what is VL1 now? If you look closely, VL1 will be equals to minus VO, right? So this will be minus VO. That's all. Or I can, yeah, minus V only, because VO is a positive number, minus VO. And it will be minus VO till 1 millisecond. Okay. And we know for the current to be constant, right? For there to be no change in current, the area of the voltage of the inductor must be 0 over a cycle. This you already know. This we have discussed multiple times. This is also known as the voltage criteria. So certainly, if the area is 0, then I can say 100 minus VO into 0.5 will be equals to VO or minus VO into 0.5. Right, both are in milli, that is equal to 0. So from here I get the value of VO. What will be the value of VO? VO will be equals to 50 volts. Very good question. This question is actually pretty good. Okay, don't undermine this question. This question is pretty good. Now VO is 50 volts, right? So if VO is 50 volts, what is IO? The current across the resistor. It will be 50 amperes only, right? Because it is a constant current, constant voltage. What is the power? Now if IO is 50, right? Who is delivering this 50 amperes of current? So IO average is 50. So as both of the converters are sharing the load equally, so half of the current will come from converter 1, that is IS1. That will be 25 amperes. And half of the time IS2 average also will be 25 amperes, because they will share load equally. So yeah, now remember, sorry, so one thing you have to understand is this is the output current, right? I'm talking about the output side. You have to consider the input side. So this is actually wrong. So IS1 is where? IS1 is here, input side, right? So basically the IS, the source current, supply current, is equals to IS1 plus IS2, and we know they are sharing the load equally. So IS will be equals to, I can say 2 IS1 or whatever, because IS1 equals to IS2, right? So I can now use the power balance equation, because there are no dissipative elements except this resistor. I know resistor is consuming the power. All of the power will be delivered by this battery only. So what is the power delivered by the battery? That is 100 into IS, and that is 2 IS1, right? What is the output power? Output power is this 50 volts into 50 amperes. So your IS will be equals to 25 amperes, and your IS1 will be equals to 12.5 amperes. That's all, right? Your IS1 will be equals to 12.5 amperes. So yeah, that's like there are two things that you can go wrong, right? So initially calculating this VO average is not that simple. So yes, there is like most of the cases you will see everywhere else in any other coaching institute, they will just use a simple formula. A simple formula they will use and they will solve it. But I have tried to solve it without using any formula. Have I touched any formula? No. Just basic formula. This power equation, power balance equation, this inductor voltage area will be 0. These basic concepts I've used. I have not used any formula. So I try to avoid any as much as formula as possible. So answer will be 12.5 amperes. Okay. Now this question, a DC to DC converter shown in the figure is charging a battery bank B2 whose voltage is constant at 150. Right, a DC to DC converter shown in the figure is charging a battery bank B2 whose voltage is constant. So B2 voltage is constant 150. B1 is another battery bank that is 50 whose voltage is constant to 50. The value of the inductors is 5 millihenry, and ideal switch such as is operated with a switching frequency of 5 kilohertz and duty ratio of 0.4. So switching frequency of 5 kilohertz and duty ratio 0.4. Once the circuit has attained steady state and assuming the diode D2 by idle, the power transferred from B1 to B2. What will be the power transfer from B1 to B2? Okay, what is the power transferred from B1 to B2? So basically they're asking what is the power delivery. So we know there are no dissipative elements here, right? So whatever the power that will be delivered by B1, let's say IB1, this is everything is average, right? From a DC voltage only average current can come out, right? AC current will not be able to come out. So it will be 50 into IB1 will be equals to 150 into IB2. This equation will always be valid no matter what. This equation has to be valid, right? So your IB1 will be equals to, so this will be 1. So your IB1 will be equals to 3/2. This is certain. Okay, that is one point. Now next point is L is 5 millihenry. Now they're asking me that, and duty ratio is 0.4. So if duty ratio is 0.4, I did see. Let's plot the graph of the inductor voltage. So duty ratio 0.4 basically means when the switch is on, then all of this voltage will come across the inductor, right? And there will be no current flowing. This diode will be turned off because this point potential will be lower than this point potential. So when the switch is turned on, that is for 0.4. So what is the time period here? Switching frequency is 5 kilohertz. Time period will be 0.2 milliseconds, right? So when this switch is closed, right? So all of this voltage will be equals to my VL, and VL is defined like this, right? So my VL will be equals to 50 till what point? Till the on period, T on. What is T on? T on is capital T into D, right? Duty cycle into D. So this will be 8.08 milliseconds. And when this is opened, right? When this is opened, then this diode will be turned on because inductor, some current has to flow through the inductor. So what is the voltage across the inductor? The voltage across the inductor will be minus 150, right? Is it possible? Yeah, voltage across. So this diode will be turned on because some current will flow, and the voltage across the inductor would be, yes, it will be, so not minus 150. This point potential will be plus 150. This point potential is plus 50. So voltage is minus 100. So voltage is minus 100. Now here something interesting will happen. So please pay attention, right? Minus 100. Now will this voltage be minus 100 till the time period, that is 0.2 millisecond? Will it be till 0.2 milliseconds or it will not be? Why? Why am I saying this? Because what is happening when when the switch is on, so it is energizing the inductor. So current is flowing in this direction, right? And as soon as the switches will be opened, what will happen? Now inductor has some potential, right? Inductor has some energy and battery also has some energy. So both of them together will try to charge this B2. Now what will happen? After a certain stage, the inductor voltage will slowly reduce because it is de-energizing. And if this voltage is reducing, so this point potential will reduce. And if this point potential reduces below 150, right? So this diode D will be turned off. And if this diode D is turned off, simply the basically inductor voltage will go to what it will go to. So what voltage will it go to? It will go to 0. Why? Because the current through it will become 0. As soon as the current becomes 0, this diode D will be turned off. And if the current is 0, it is not changing because current cannot flow in this direction. It is not changing. So di by dt is 0. Hence VL is 0. So voltage across the inductor will become 0. Now let's see whether that will happen or not. So for that we have to plot the current graph. So if I plot the current graph, right, from 0, this is my current graph, I of t and t, right? So this will be going from 0. So voltage is constant. What is the voltage? Voltage is 50, right? So we know that my dIL by dt, the slope of the current, right, is equals to VL by L, voltage across the inductor by L. L is 5 millihenry. So this slope will be basically 10 ampere per milliseconds. Okay, because this is already in milli, right? So it won't matter, per millisecond. So 10 ampere per millisecond. So I am going till 0.08 milliseconds. So it will be actually 0.8 amperes. And then as soon as the voltage will become what? Minus 100, right? This voltage will be minus 100 if you see. Here I have plus 150, here I have plus 50, so this is minus 100. So voltage will start to reduce. And as now it will reduce at a much faster rate. Why? Because now what is the slope? Slope is minus 100 upon 5 milli, right? Minus 100 meaning VL. VL is now minus 100 upon 5 milli. So it is minus 20 ampere per millisecond, right? So it will go to 0 in how much time? So currently it is at 0.8, right? So in how much time will it go to 0? So this I can easily calculate. So if it is reducing by if it is reducing by 20 ampere per millisecond, so in about 0.4 milliseconds. In about 0.4, because if I multiply 0.4 milliseconds with this, I will get back to 0.8. Sorry, 0.04. 0.04 actually, yeah. So in about 0.04. So this period was till 0.0 milliseconds, and this period, right, the decaying period. So this slope is what? This slope is 10 ampere per millisecond, and this slope is minus 20 ampere. So it will decay faster. So if it took it 0.8 milliseconds to reach to 0.8 amperes, it will take it only 0.04 milliseconds to reach to 0 ampere again. So 0 in 0.04 milliamperes, or exactly at t equals to 0.12 milliseconds, right? Because 0.04 plus 0.08 is 0.12 milliseconds. This will be actually 0. Okay, after this 0. Why 0? Because of course diode, although the current will want to go into the reverse direction, but diode will not let it do that, right? So current will always be 0. So what is happening basically at t equals to 0.12 milliseconds, the current will go to 0. So hence the voltage also will go to 0. How can I verify it? You can also calculate this area, right? You will see how can I verify this time is correct. If you calculate this area will come out to be 0. Do it now, do it, right? This area of VL graph will always be 0. You do it now. Okay, so that's how you can verify whatever time you have computed here is correct. So trust me, in any other coaching institute they will just use some formula. We're not using any formula. Now what are they asking? Actually we have not even came to the problem. Okay, cool. Now they're asking me what is the power transferred from B1 to B2. Now one interesting fact is from 0 to 0.08, right? Again this cycle will be repeated after what? After 0.2 milliseconds this cycle will be simply repeated. right? So what is happening over here is that if you see that from 0 to 0.08 this switch is closed, so battery V1 is delivering all the current, and when this switch is open, then again the battery V1 is connected. So battery V1 is always connected to the inductor, so the current across the inductor is same as the current across the battery B1, not the B2, the B1, because B2 is for a certain period, B2 is turned off right here when the switch is closed. So if I am able to compute the average inductor current, that will be my average battery current, and that will help me the power transferred, power delivered, right? So I can compute that this will be equals to IL average will be this area of this graph, so that is half into base, that is 0.12 into height, that is 0.08. Remember, your time is in milli, right? Your time is in milli, so your current also will come in milli, but you're computing the area and you have to divide by the time period as well, right? That is the average current. So you're doing by time period, and time period also is 0.2 milliseconds, so milli will be cancelled. Don't worry. So this will be 4 times this will be 2, so this will be 0.24 amperes. So your IB1 average is 0.24 amperes. Okay, so that's a 0.24 amperes. So if my IB average is 0.24 amperes, so my power delivered by the battery B1 would be 15 to 0.24, that would be 5 into this, so 5 is 0.1, 1.2, 12 watts. Okay, so power delivered by battery B1 would be 12 watts. So 12 watts is the answer for this question. There are many formulas that you can use, but I will not recommend using any formula. Similarly, same thing you can use for our output. So from this, right, you know what is the battery V1 current, right? You'll be able to compute the battery B2 current as well. So everything you will be able to do. So this question was very beautiful, very good. Without any formulas, we try to solve this question. Let's solve the next question. A DC to DC buck converter operates in continuous conduction mode. Whenever they say buck means step down converter, and it is operating in continuous conduction mode. So I can directly say, because it is operating in continuous conduction mode, my VO average will be equals to alpha into VS, right? VS average. So it has an input voltage of 48 volts. Okay, so its input voltage is 48 volts, and so VS is 48 volts, and it feeds a resistive load of 24 ohms. Okay, the switching frequency of the converter is 250 hertz, or I can say 0.25 kilohertz for my convenience. If the switch on duration T on is 1 millisecond, what is the load power? It's pretty simple. You need to find out alpha and Vs. Vs is given to you, that is 48 volt. Alpha is what? Duty ratio, T on by T. So alpha is T on by T. So I know T on is given to me 1 millisecond. What is T? T will be the inverse of the switching frequency, the time period. So inverse of this will be, your capital T will be inverse of this, that is 4 milliseconds. So you got your T. So your alpha would be T on by T, that is 0.25. So you got your duty ratio, you got your uh, Vs. So it will be 0.25 into 48, that is 12 volts. So your VO average is 12 volts. Now if your load is purely resistive, and we know that it is operating in continuous conduction mode, so I have a DC voltage connected across the load, that is 12 volts, right? So your answer will be 12 square by 24. That's all. The power consumed by the load will be 12 square by 24, because it is a constant voltage. It will be V square by R. So 144 by, so it will be 12 to, and another 12 is a 6. So this will be 6 watt. So 6 watt will be your answer for the question. I hope there is not much of difficulties here. Hold on a second. This is T on is 1.54 milliseconds. So yeah, hold on a second. I am just thinking. It is operating in continuous conduction mode. Just give me 1 second. Okay. It is operating in continuous conduction mode. Okay. The converter is operating in continuous conduction mode. If it's a buck converter, so it will be on and then it will close. But if it is operating in continuous conduction mode, there will be inductor that will always let the current to flow. So yeah, they have told me that it is operating in continuous conduction mode. So yeah, 6 watt will be answer. If this word was not written, right, it is not if it is not operating in continuous conduction mode, that means what? So basically what is happening, so this is my chopper circuit, the most basic chopper, without any inductor, anything, right? The most basic step down chopper. Now what will happen if that limit it is operating in continuous conduction mode? That basically means whenever the switch is open, right, the load will still have some current. How is it possible? It is possible only if there is an inductor, like it is like a filter, right? Okay. So if there is inductor, what will happen is okay, there needs to be a diode as well. There needs to be a diode as well, right? So what will happen is once this switch is open, right, so all of the current, right, that it was taking will flow through here. So this inductor will help retain the energy. So that's the task of inductor basically. So answer will be 6 watts. That's how the current is continuous. That's how these equations come. So this if it is operating in continuous conduction mode, then you can simply blindly apply the formula. Okay. Yeah. So the next question, in a DC to DC converter, the DT ratio is controlled to regulate the output voltage at 48 volt. So VO average is 48 volts, right? Okay, hold on a second. I'm just thinking something. Just give me 1 second. So this will keep the inductor on. So this will turn it on. Okay. Yeah, I think this is fine. They should have properly provided the circuit if they want a proper answer, right? Because I'm thinking, what if the current is not continuous? But they should be providing the circuit. Okay, fine. V average is this. The input voltage is 24 volts. So it is a step up chopper, right? Input is 24. At the output, uh, we're getting a higher voltage. So always when we get a higher voltage, so what we do? We initially energize the inductor. This I have taught in my full course, right? So we will have a switch here with which first I will energize the inductor. Then after energizing the inductor enough, I will put all whatever voltage I have in the load side. Okay. So yeah, assume ideal components and very large output filter capacitance. So output filter capacitance is very large. That basically means the output voltage will be constant at 48 volt. The converter operates at boundary between discontinuous and continuous modes. The value of the boost inductor would be. So it operates in the boundary. Okay. So what does they mean by boundary condition? Boundary basically means the current across the inductor will just touch zero. It will never go below zero, but it will certainly touch zero. So how will the current across the inductor will look? So once this switch is closed, the voltage across the inductor is 24, so it is energizing. So it will start from zero and will increase to some peak value. What is the value? You might ask, right? That will be basically that we can calculate basically, but we don't know the L. So what is the time? Time is the time till which the switch is closed. So I know the switching frequency, uh, and I don't know anything else, right? Switching frequency FSW is 50 kilohertz, right? And my battery, like the output power is 120 watts, right? Output power is 120 watts. So P out is 120. Now, what we can do is we can actually calculate the average current. Yeah, that will be actually very helpful. So what will be the average current of the supply? So because all the elements are ideal here, there will be no losses. So whatever is the input current, input voltage, same will be the whatever is the input power, same I will get at the receiver at the output, right? So there are no losses. So 120 will be equals to my input voltage into the IL average, because this inductor also will always be intact with the supply. So IS average will be same as IL average. So oil average will be 5 ampere. Okay, so this is again a very interesting data point. Why I will explain. So what I've done, they asked me the value of the Hooke's inverter. Yeah, this is important. So let us assume that this reaches some peak value IP, right? Then again it discharges. Now what will be the discharge rate? Charging rate was basically, because the what is the voltage? It is 24, right? So my DIL by dt when the switch is closed, it will be 24 by L. What is the DIL by dt when the switch is opened? So this point potential, right, if this diode is assumed to be on, is plus 48. This point potential is plus 24. So DIL by dt will be minus 24 by L. So it is exactly symmetrical. So at t equals to, so okay, what is the, so what will happen actually if it is exactly symmetrical, right? So it will take same amount of time to go to 0. So this point of time will be half of the total time period. So what is the time period? So if f switching is 50 kilohertz, your total time period would be, so 1 by 5 is 0.2, 1 by 50 would be 0.02 milliseconds, right? Or I can say this would be 0.02 milliseconds, right? So into, if I do 1000, 0.2 to 20 microseconds. This will be 20 microseconds, and they have asked in microhenry only. So this overall duration is 20 microseconds, and half of the duration would be 10 microseconds. Now I know this, I know the average value, right? So basically half into IP into 20 microseconds divided by the 20 microseconds, right? The average value would be equals to the 5, because IL average is equals to this average of the graph, that is area by time period. So that would be IP by 2. IP by 2 is equals to 5 ampere. So your IP is equals to IP equals to 10 ampere, right? So your IP is equals to 10 ampere. So now what you can do is that IP is 10 amperes. So I can replace it over here, right? So what is DIL by dt? DIL by dt is the slope. So DIL by dt, right? So what is the change in the current here? 0 to IP. So it is IP minus 0 by dt, that is change in the time is 10 microseconds. That is equals to DIL by dt, that is 10 microseconds, that will be equals to that is given, right? That is 24 by L. So I will get the value of inverters, because this is in micro, so I don't need to worry. I can directly keep it in micro only. IP I already know, IP is 10, right? So IP is 10. So it is 10 by 10, that is 1. So actually your L is 24 micro Henry. This is your answer. So without touching any formula. So you will see in any other solution there will be formulas only, but I have not touched any formula. Okay, here no formula used. So if you are enjoying this video, hit the like button. So yeah, 24 micro Henry will be the answer. Let's solve the next question. So in DC to DC converter, the switch Q is switched at a frequency of 10 kilohertz with duty ratio of 0.6. All components of the circuits are ideal. Okay, so DC to DC converter circuit is shown. Switch Q is switched at a frequency. So F switch. Do you know what kind of converter this is? You are not realizing it, but you know. So 10 kilohertz duty ratio alpha is 0.6, alpha or D, whatever you feel like writing. All components of the circuit are ideal, and the initial current in the inductor is 0. Okay, energy stored in the inductor in millijoule at the end of 10 switching cycles. Okay, so let's first understand in one cycle what will be the energy stored, then we can obviously calculate the 10 switching cycles. So do you know what this is, what kind of converter is this is? I'm not able to figure out, so don't need to worry, just solve with basics, right? So what does duty cycle mean? Duty cycle means the ratio of T on over capital T, basically the period for which the switch is on, right? I know 0.6, I know switching frequency, I can easily calculate what is capital T. Capital T would be 0.1 milliseconds, right? 0.1 milliseconds. So your T on would be This is your alpha, right? So T1 would be alpha into T, that is equals to 0.06 or milliseconds, or I can write it to be 60 microseconds. Okay, that is what your T1 is equals to, right? Now T1 I got. So if I replace, when the switch will be turned on, right, what will happen? The voltage across the inductor will be what? It will be plus 50. The voltage across the inductor will be plus 50. And if the voltage again is constant, then the current also will increase linearly, and we know initially the current was 0, so it will increase linearly till the point what? Till 60 microseconds. 60 microseconds, right? What will be this value of the current? That also we can calculate. That will be basically, so the VL is 50, VL by L, right? That is 10 milli. That is equals to your I. So VL equals to LDI by dt. That is the formula that I'm using by change in T, right? So delta I into delta T, that is 60 microseconds. So actually this is in micro, that is a problem to us, right? So this 0 will go away, that 60 will go there, 6 will go there, so this will be 300. I have to multiply 10 to the power minus 3. So your I would be 0.3 amperes. Okay, so this will be 0.3 amperes, right? Then what will happen after it reaches 0.3 amperes? Then basically then this switch will be turned off, and as this switch is turned off, the battery will not deliver any current, right? This current is 0, so inductor still has some current, so it will try to keep the current constant. So what will happen? It will turn on this diode, it will turn on the second circuit. Now this is the voltage across the inductor, right? Plus minus VL. Now as soon as it will turn on the diode, what will happen? The voltage across the inductor will be minus 50. You apply the KVL, voltage across the inductor will be minus 50. So this voltage will be minus 50. So if this voltage is minus 50 and it will remain minus 50 till the point diode is turned on. So it is very symmetric, right? And okay, it is very symmetric, but my alpha is on till 0.6. So what will happen here is that, so as it is symmetric, right? So my time period ends at 100 microseconds. So if it took, like, because now what is the slope in the current? It is minus 50 by L, right? If you see, when this diode is on, the voltage across the inductor is minus 50. So now the change of current, right, is minus 50 by L. That is the change in current. Okay. Now, so again, so it will take it 60 microseconds to reach to totally 0, but it will not reach to 0 because we'll change the switch circuit again at t equals to 100, right? So what is this current? So we gave it only 40 microseconds. So if I multiply this by 40, right, this will be minus 0.2. So what you will do? What is the change in time? Change in time is 40 microseconds, right? So your delta L would be minus 50 into 40 divided by L. L is, remember, L is 10 millihenry, right? So this will be basically 0.2 minus 0.2 ampere. So change in current is minus 0.2. So if previously it was at 0.3, now it will reduce by 0.2, that is 0.1. Now the current will be 0.1. So after the end of the first cycle, the current across the inductor is 0.1, and this cycle will repeat. So what will happen? Again, there will be a delta L of 0.3. So from 0.1 it will go to 0.4. Again the current will reduce, this cycle will repeat. You can do the analysis, and now at the end of the second cycle the current will be 0.2. So at the end of the 10th cycle, what will be the current? It will be 1 ampere. So at the across the inductor, I'm talking about the inductor, right? At the end of 10th cycle, IL 10t, right, will be equals to 1 ampere. So what is the energy stored in the inductor in millijoule? It will be half L, that is 10 millihenry, into I square, that is 1 square, right? So it is already in millihenry, so energy will already be in millijoules. So this will be 5 millijoules. Pretty very beautiful question. Again, the examiner does not want you to ask from any formulas. They want you to solve it with basics. So your answer would be 5 millijoules. That's all. Let's solve the next question, right? Next question is this: consider a boost converter shown. Switch Q is operating at 25 kilohertz. So your time period is so it is 25 kilohertz, right? So if it was 0.25, it will be 4. Now it will be 0.4. Now it will be 0.004. That is actually 4 microseconds, right? If I'm not mistaken. So 0.025. No, I think 40 microseconds. Sorry, 40 microseconds. This will be 40 microseconds, right? So 1 divided by 25 is in milli. Yeah, 40 microseconds, correct. Now our duty cycle is 0.6. And what kind of chopper is this? Again, this is a boost chopper, right? First we're boosting the inductor, then when the switch is opened, then all of this, both this voltage together, is delivering to the load. Under steady state condition, the average resistance are in seen from the source. What is the average resistance seen from the source? So like this is not a certain standard term, but the average resistance will be whatever the voltage across the source, average voltage, whatever is the current across the source. So Vs average by Is average. Vs is already DC, so if I write average or don't write average, it does not make any difference. So yeah, this is my Rin. So I know my Vs, I have to compute my Is average. So for that, first of all, I need to check whether my current will be continuous or not. So okay, let's assume the continuous case. Okay, let's assume the continuous case and we'll see. So if the current is in continuous case, right? So this will deliver some current. So what will be the voltage across the inductor when the switch is closed? It will be the input voltage. So this will be 15 volt. Till the point, it will be 15 volt. Okay, it will be 15 volt. Okay. Now when the switch is opened, now if this diode is turned on, then the voltage will be, if this is some VO voltage average, if I assume this voltage is constant, this voltage will be, now we can actually compare, right? We can compare with the time constant. So when this switch is open, right, what is R into C? Because it is essentially a parallel load. So R into C is basically 1000 microseconds or 1 millisecond. Okay. So what is 4 tau? 4 tau is 4 milliseconds, right? 4 milliseconds. Now, interesting fact is your time period itself is 40 microseconds. It is almost 1 by 100. Your time period is 1 by 100. So your T is much less than 4 tau. So whatever the voltage there is across the inductor or across the capacitor, this will never discharge, right? So this voltage will always be constant. So I can safely assume that this VO voltage will be constant voltage, okay, by comparing the time constants. So the voltage in the second case across the inductor will be, so assuming VO is greater than the input voltage, it will be 15 minus VO, okay, and this will remain till the point of, now till what point it will remain, that we will discuss, okay. So okay, so let us assume, okay, let us see what is the change in current when this switch is closed. What will be the change in current across the inductor? I'm talking about the inductor. So change in current, right, will be delta L will be delta IL by delta T will be equals to L DIL by dt. Sorry, L DIL by dt will be equals to VL. So delta L by delta T will be equals to VL by L. So VL is what? Voltage across the inductor, that is 15 upon the inductance, that is 1 milli, right? And delta T is what? Okay, alpha is given to me, right? So what is T on? T on would be 0.6 into 40, that is 24 microseconds. So this is 24 microseconds, right? So it is 24 microseconds. So your delta IL will be equal to 15 into 24 micro, 15 to 24 micro and divided by 1000, right? Because it is in micro and that was milli. So 15 into 24 divided by 1000, that is 0.36. Okay. Now, okay, I don't know what is the voltage, average voltage across the load. Okay. And nowhere it is mentioned that, no, under steady state condition, the average resistance. Okay. How do I understand? Okay. The thing that I'm trying to figure out, okay, this voltage will be constant. Hey, this voltage is constant. What is this voltage? So nowhere it is mentioned, right? So do I have to assume continuous conduction or what? That is what I'm trying to figure out. Okay, let's assume continuous conduction. If I assume continuous conduction, right? So this, if I assume continuous conduction, that means this diode will be always be on till the point this switch is off, right? This diode will always be on because I'm assuming inductor has continuous conduction. That means this will always be flowing till the point next time the switch will be closed again, right? So this voltage across the inductor will remain same till the point of t equals to 40 microseconds, right? 40 microseconds. Okay. Now from this I know obviously the equal criterion, that the positive area will be equal to negative area for inductor voltage if the current is continuous. So this will be 15 into 24 micro, that is basically, that is what we have calculated here, isn't it? No, that is not what we have calculated. So 15 into 24 essentially will be equals to the negative area, that is 15 minus VO into 16, right? So this will be 32. So this will be 45 to the 30 minus 2 VO. Okay, it is coming out to negative. So then it is a problem. VO cannot be negative, right? So there is no continuous conduction. So as it is coming out to be negative, right, there is no continuous conduction. So if you see VO itself is coming out to be negative, which is not possible. VO cannot come out to be negative. Load cannot deliver. Okay. So there is a problem, right? There is a problem. So what will happen is this diode will be turned off much earlier. As soon as this diode will be turned off, what will happen? The voltage across the load will be same, but this capacitor will deliver, but this diode will be turned off. As soon as this diode is turned off, the current across the inductor is 0. So there is no change in current. If there is no change in current, the voltage also will be 0. So this will be 0. Now I have to find out this time. Do I have to find out this time? Yes, I have to find out this time, because I have to find out the average inductor current, right? Yes. So what is the time? So the time, right, this time will be what? So this time will be the point till which the area will be 0. Why? What will happen basically? If I draw the inductor current, right? So whenever the voltage is positive, the current will increase, and whenever the voltage is negative, current will reduce. And at this point t, the current will go to 0. As soon as the current will go to 0, the diode will be turned off. So inductor will stop conducting, and the voltage will remain at 0 voltage. Okay, this is what is happening. Again, this cycle is repeating in the next time period. So that is what is happening here, right? So we have to compute this, right? So for that, what essentially happens is this area is 0. Okay, these things I've taught in my like comprehensive course, so I'll not go over it again. So if area is 0, this will be 15 into 24 micro, that will be equals to 15 minus VO into T minus 24, right? So from this, I think we will be able to calculate. Okay, so okay, there are many things here. So okay, there are two unknown variables. How will I calculate this? Uh, this one is this area criteria. What is the other criteria? Okay, the other criteria would be whatever is the input power that I'm delivering, right? All of it is going to the resistor only, because there are no dissipative elements. So the input power, right, is 15 into IS average, and your IS is nothing but IL, right? It is in series. That is equals to my VO average into IO average. Now the interesting point for a resistive load is your VO average will be equals to 10 into 10 into IO average, right? VO average will be equals to so yeah. So from this, I can actually calculate. What can I calculate? Will this help me anyhow? Okay, no, no. So let me write it in terms of VO average only. That will be, yeah, that will be helpful actually. But will it be helpful? That is what I'm thinking. How will it be helpful? How will it be helpful? Mm, it's 0.36, changing current is 0.36. So okay, I got it. Okay, I got this. So we have calculated the changing current, right? So because we know it is discontinuous mode, so this peak, right, this peak will be what? This peak will be 0.36 only, because that is the changing current, right, from t equal to 0 to t equals to this 24 microseconds. Now what do we know? What things do we know? uh, I do know what is my IL average. What is my IL average? So my IL average is, in terms of VO average, I can write. And will that be helpful here? I think yes, I think it will be helpful. Like, this question is becoming a bit tedious, but I think we will be able to crack it, right? So just give me 1 second, right? Is it continuous conduction mode or not? That is what I'm trying to figure out. So we have 16 micro, so this is into 3. I'm just figuring stuff out. Okay. No, this is correct only. 15 minus VO, that is correct. Oh, such a silly error I've made. So this will be plus, right? So the area, right? I always make this error. So this is positive area, this is negative area. That is fine. But actually, what is happening? If you want to write this positive area equal to negative area, you have to write the negative term. So 15 minus VO is the negative term. You have to write in the other side. So like, this is just a area problem. Okay, that's what I was thinking. That question should not be that difficult. So yeah, if it is discontinuous condition, then you have to solve it like this, and the question will be lengthy actually, to be honest. But so what I'm doing, I'm just adding up the area. This is the area, this is the next area, right? I'm adding these two areas up. So 15 minus VO is negative, I agree. So what is happening? Let's say VO is 20, right? So 15 minus 20, that is minus 5. So this area is negative only, right? So that's why you don't need to write negative sign here again, otherwise it will make it positive. Okay, so this must be equal to 0, right? Now it is fine. Now if you see, your VO will come out to be, this is 5 into 75, 2 VO. So your VO actually will come out to be 75 by 2. that is 37.5 volts. Okay, that is what your VO is equals to. Great, we got our VO. Okay, it is continuous conduction because your VO is coming out to be positive, so hence it will be continuous conduction. Okay, so it is continuous conduction, so we don't have to consider all these cases, right? Okay, otherwise it will become very lengthy, trust me. Okay, so VO is continuous conduction. Now these things we can delete. Now it becomes very simple, right? So if I know VO, right, I know IO average. IO average will be VO average by 10, right? Because I know R. So IO average is 3.75, and if I know IO average, right, I just certainly know IS average. IS average will be VO average into IS average. VO average is 37.5 into IO average. IO average is 3.75 divided by VS. So what is VS? VS is 15, right? Okay, so yeah, now we can solve it. So this will be 37.5 into 3.75 upon 15. So that is 9.375. amperes. Okay, that is the current basically, but they have asked me the resistance, right? So it will be Vs average upon Is average, right? That will be equals to if Vs average is 15 into Is average, that is 1.6 ohms. So 1.6 ohms will be your answer. This became a bit lengthy due to my own own doing. So yeah, this is the simple answer to this question. Yeah, so let's move on to the next question. Just give me 1 second. Yeah, consider the buck boost converter shown, right? Consider the buck boost converter shown. Switch Q is operating at 25 kilohertz. Okay, switch Q is operating at 25 kilohertz. And duty ratio is 0.75. Duty cycle, assume diode and switch to be idle, then under steady state condition the average current flowing into the inductor, what is my IL average? Now this is not that simple to calculate as you think. Okay, not that simple. Okay. So few things to note here. The switching frequency is 25 kilohertz. So what is the time period? Again, time period is 40 microseconds, right? And what is the time constant when the diode is like open? This diode is open, it becomes simple RC circuit. So which is R into C, that is 100 micro into 10, that is 1000 microseconds, that is 1 milliseconds, right? So this difference is again very large. It's almost 5 into 5 into 5, yeah, 25 times, 25x, right? So your tau, right, tau itself is much greater than the time period. So again this will not get enough time to discharge, so capacitor voltage will almost be constant, almost be ripple free. So VO is constant, so hence IO also is constant. That is point 1. Okay, VO is constant, IO is constant. What else can I compute? So again I can see I can calculate the I can draw the voltage across the inductor, and that will give me an idea whether the current will be continuous or not, or there will be discontinuous mode of conduction. Voltage will like the inductor voltage will give me good idea. So inductor voltage, right, when the switch is on, it will be directly input voltage, right? This is short circuit direct input voltage, that is equals to 20 volts. it is equals to 20 volts. And this is my hold on a second. So this is my 20 volt 1 millihenry. So duty cycle is given, right? So duty cycle into my capital T will be my on period. So 0.75 into 40, right? So this will be 4 into 7.5, so 30. So this will be 30 microseconds almost. So for 30 microseconds, the voltage will be Vs 30 microseconds. And let's assume that there is some continuous conduction. So then the voltage becomes negative. Assume that VO is greater. Okay, VO can be greater or VO can be less than the input voltage, but let's assume that VO is greater. So if VO is greater than this, so it will be this, right? That is, this will be 20 minus VO. Okay, that will be the voltage 20 minus VO. Okay, so now, and this will end at 40 microseconds. So let's calculate the value of VO from here. Right? So okay, hold on a second. When this switch is turned off, right, what is the voltage? The inverter voltage. The inverter voltage is VO itself. Sorry, I'm extremely sorry. Inverter voltage is VO itself, right? Inverter voltage is VO. So minus plus, yeah, inverter voltage is VO itself. Okay. Okay, one more thing. Remember, current will flow like this, right? So your VO voltage is like this actually. Because this diode, if this diode needs to be turned on, current will flow like this. I know the name of this converter, it is buck boost, it is already written. But without knowing the name, without knowing any nomenclature, still we can solve it with basics. So this current will be, current will be flowing in this direction. So voltage polarity will be like this, and inverter voltage polarity is like this, right? Plus minus VL, because this was my initial assumption. So in this case, when the diode is on, when the switch is off, the voltage across the inductor is minus VO. It's negative of VO. So actually this is wrong. That's why you don't blindly just write stuff, right? You see the circuit. So it is minus VO. Now the part is interesting. It is minus VO. So the area will be 20 into 30 micro minus VO into 40 micro, right? Equal to 0. For continuous conduction, the average voltage across the inductor will be 0. So from this, VO will be equals to 15 volts, which is fine, right? We can see, like, if you know the formula for buck boost stopper, it is V over Vi or Vs equals to alpha by 1 minus alpha. Like, I don't recommend remembering the formula, but you can see that this will match. So what is alpha? Alpha is 0.75, right? So 0.75 upon 1 minus alpha, that is 0.15. Sorry, 0.25. So this will be 3, and Vs is okay. Formula is not matching. That's quite interesting. It should match actually if it's a buck boost chopper. Okay, 3 into this. Oh, why am I writing 40 here? Okay, why am I writing 40? This, I've write this distance, right? That is 10. Okay, that's what I was thinking. Oh my god, what I have a mess up. So this will be 3 times 20, that is 60, which is exactly same here. VO is 60. Okay, that's why you check with other formulas to verify whether you have done something wrong or not. So this was the voltage actually. So all this was done just to check whether the current is continuous across the inductor. Current is continuous across the inductor. Now, what is the average current across the inductor? There are many ways to solve this. First way is to certainly plot the current waveform, and that will be the most straightforward way, right? IL. So when it is 20, right, current will increase So it is continuous. Current will increase from some value and it will go to some peak value, then again it will reduce from the peak value and come down when the voltage is negative, that is VO is minus 60, and it will reduce at a much faster rate and del IL will be same. But this will actually not give me the average value. That is what I don't want. Okay. Okay. How can I calculate the average value? This is the current that is incoming here. So some current is flowing here, right? Then the switch is turned off. And so your IN will be equals to your IL. Now, a few things you have to assume that what is delta IL? What is my delta IL? Delta IL I can calculate, right? So delta IL by delta T will be equals to VL by L, correct? L is 1 millihenry. So in the duration during the switch, when the switch is on, delta IL will be equals to VL. VL is 20 upon L. L is 1 millihenry into delta T. Delta T is 30 micro, right? So I have to divide by 1000 as well, correct? So this will be 2 zeros will be gone, 6 by 10, that is 0.6 amperes. Okay, so delta IL is 0.6 amperes. This is fine. So I got delta IL, right? So I got the delta IL. This is my delta IL, and if I know the delta IL, I know this width, right? I know this width, correct? This width is nothing but 40 microseconds. This width is nothing but 40 microseconds. If I know this width, I can compute the area of this particular part. But what about this rectangle? How do I know this? So what is the minimum current? What is the minimum and maximum current? How do I know that? How do I compute that? Okay, so is there any relation? That is what I'm trying to think of. So certainly one relation that we know is whatever is the input power, same will be the output power, because there are no uh, energy dissipating elements in between the converter. So it will be 20 into IN average will be equals to VO average into IO average, correct? And I already know what is my VO average, correct? VO average is 60 volts. 60 volts, right? If VO average is 60 volts, what is IO average? It will be 60 by 10, that is 6 ampere. That is 6 ampere. So your IN average will be equals to 20 V average into IO average, that is 60 into 6 divided by 20, that is 3 into 6, that is 18 amperes. Now the interesting fact is, let's assume that this switch is off. When the switch is off, right? So some current is flowing, there is some ripple, you can see the current is reducing. So all of this ripple, right, reducing in current will be accounted in the capacitor current. None of it will be reflected in the load side, because load side the voltage is constant due to the capacitance, hence the current also will be constant. So all of this current ripple will be accounted in the capacitor, right? Ripple current will be accounted in the capacitor and the constant current will be delivered by the inductor. So what is that constant current? That constant current is 18, so not 18. During when the switch is on, right? When the switch is on, it is simply 6 ampere. Now here, how will we calculate the average inductor current? So if you notice one thing, inductor is always conducting, right? So either inductor is equals to IO plus IS. Can I write this? Can I write this? Technically, technically no, actually. Technically no, because your inductor current is equals to roughly source current for t greater than equal to 0 till greater less than equals to alpha d. That is basically 30 micro. And it is equals to IL, that is a load, sorry, it is equals to I naught for t less than equals to 10 micro, 40 micro to greater than equals to 30 micro, right? That is the scenario, right? So now I think it should not be that difficult for you to compute, correct? Because the ripple has been taken care of. So roughly if you calculate the average, so it will be is, right? What is is? It is 18 ampere. Now remember, 18 ampere is the average value, right? Is average is 18 ampere. But what is the, so if I plot the input current, right, in or is, whatever you want to say, if I plot the input current will be roughly like this, right? And then it will suddenly go to 0, and then again input current will be roughly like this, right, from 0 to 30 micro. And your load current, so not exactly the load current actually, so it will be the it will include the this what do you say, this capacitor current plus the load current IO. This will be something like this. So what I'm plotting this current, let's say this diode current, right? I'm plotting this diode current because your inductor current IL is equals to what? It is equals to ID, the diode current, plus your input current or the switch current, right? So what I can certainly say, although I prove it as well, your average current of the inductor will be equals to ID average plus IN average. Okay, that is certain, right? Your average current across the inductor will be equals to ID average plus IN average. Why? Because this equation is, this KCL is always valid. The switch current is same as the input current, they are in series. So from here you can directly say like what is the answer. So your diode current is what? Your diode current is actually combination of the capacitor current and the uh, load current, and we know the average value of the capacitor current is 0. It follows the same property as the inductor, right? So average of the capacitor current is 0. So IL average will be ultimately equals to diode current average, that is equals to IO average only, right? Because average capacitor current is 0, because ID is IC plus IO, but IC average is 0 plus so your IL average will be equals to actually I average is I average is 6 amperes. In average is 18 amperes. So your answer would be 24. This is your answer. But if you want to prove, you can prove from here as well. If I plot the diode, right, diode current, what will be the diode current? Diode current will be somewhat like this. So it will be because this will be turned off, right, when the switch is on. So capacitor will deliver the current. So diode current will be 0 from 0 to 30 micro, right, and then from till 30 till 10 micro, current will be somewhat like this, right? So 30 till 40 micro seconds, current will be somewhat like this. If you compute this average value, so this is what is, so this is how we compute the ID average, right? Because this is the part 0, so ID average will be this only. So if you compute the average of this, right, so your overall inductor average current will be addition of this average value and this average value, and we have already established what is the average value here, right? That's why. So although this is like a very short question, but understanding why this equation is valid, that is the most important part. Understanding why is this equation valid, right? Let's solve the next question. The steady state current flowing through the inductor in a DC-DC buck boost chopper. So it is a buck boost chopper that is given in the figure below. The peak to peak ripple of the output voltage, right? So if it's a buck boost chopper, so you know the circuit diagram of a buck boost chopper. I will have the switch here. I will have the inductor here. then I will have the load here, right? This is Vs, this is the inductor, this is the voltage Vo, right? And of course there is a capacitor. Okay, now what they're telling me, what is the value of the output capacitor in microfarad if the ripple in the output voltage is 1 volt? So when will this ripple occur? So whenever this switch is turned off, right? Sorry, whenever the switch is turned on, so it will energize the inductor. So this diode will be off automatically, no current will flow through this diode, so there will be only this C and the load. Assuming if it's R load, then it will obviously discharge. We don't know exactly what kind of load it is, but certainly it will, the capacitor, whatever energy it has, it will deliver to the load. That is certain. And while doing so, the capacitor voltage will reduce, certainly. And that's what they are telling me, that the ripple from the peak value, whatever was the peak capacitor voltage, to the minimum value is 1 volt. But we will assume the load current to be constant. We will assume the load current to be constant because nothing is mentioned. I will assume the load current to be almost constant. Okay, I will assume that load has a high inductance and it is almost constant. So if the load current is constant, I can do something with that, right? I will say what I can do. So what is IC? IC is C dVc by dt, right? So I know load current is constant. I know delta V. I know delta T. What is delta T? Delta T is the duration during which this switches on. And what is the duration? That is this duration. When the switch is on, then the inductor current will increase. That is 20 microsecond. So I know delta T, that is 20 micro. I know delta V, that is 1 volt. I don't know C. Do I know IC? IC will be what? IC will be IO average. Right? That is the constant value of the load current. How to calculate IO average? So I don't know Vs. All I know is this. Okay. So in the previous question itself, we have solved a similar pattern, that my IL average is what? This we have derived as well in the previous question. IL average is IO average plus IS average. Okay. And for a buck boost chopper, as we can see, current is continuous, current is never going to zero. Hence, we can use formulas. Okay. Here, first time I will use some formulas. That so we know this, right? VO by Vs for a buck boost chopper is alpha by 1 minus alpha, and the current relation is just the opposite because they follow the power, right? Power must be same. That's why. So Is by IO would be alpha by 1 minus alpha, and alpha is given. It is hidden. Alpha is hidden. What is alpha? Alpha is the duration for which this switch is on. That is 20, right? So alpha is what? Alpha is T on upon capital T. This will be 20 upon 50. So this is 0.4. So alpha is 0.4. This information is hidden to us, right? So I can directly say, so I can directly write what is IL average. IL average I already know. IL average is very easy to calculate. What is IL average? What is IL average? IL average would be, hold on a second. This plus this. I have to compute. What do I have to compute? Okay, let's not compute IL average. Okay, I can directly compute what is my IO average, right? I can directly compute what is my IO average. How can I directly compute? So during this stage, right? Can I compute my average? That is what I'm trying to figure out. Yeah, during this stage, this is the stage where the current is across the load, right? When the switch is off. I'm just trying to think something. 20 into 50 plus into yeah. we'll calculate IL average only. We'll calculate IL average only. So what is IL average? IL average would be this 12. This is the first rectangle, right? And this is the triangle. Okay, what is the height of the triangle? 4 amperes. Width is 50, right? So 12 into 50 plus 4 into half into 4 into 50 micro upon the total time, that is 50 micro, right? So basically your IL average is 14 ampere. So IL average is 14 ampere, and okay, and I can compute my IO average. So IO average, this will be 1 plus IS average. IS average is alpha into 1 minus alpha IO average. So I can use this formula, right? So this formula basically here, this will be equals to IL average. IL average is 14, right? So your IO will be 1 minus alpha alpha. So it is simply 14 into 1 minus alpha, right? Alpha is 0.4, so it is 14 into 0.6. So 6 would be 8.4. 814 amperes. Right, so it is 8.4 amperes. So we got our IO average, and yeah, that will be equals to IC only during the discharging phase. So this equation will be 8.4 into C into delta V, that is 1, upon delta T, that is 20 micro. So your C will be 8.4 into 20, that is 84 into 2, that is 168 microfarad. Okay, 168 microfarad. This will be your answer for the question. Okay, bit difficult, like to understand exactly how to solve. That's why you are watching this video. That's why you are watching this video, right? To understand how to solve a particular pattern of questions. Let's now move on to the next question. This one. So again, I'm not using any formulas, right? I'm trying to go by basics. That's why it is taking us more time in the chopper section. The chopper circuit uh, shown in the figure feeds power to a 5 ampere DC constant current source. Okay, it feeds power to a 5 ampere DC constant current source. We have a chopper circuit, which is not a standard chopper circuit as such, right? Now what they want us to calculate is the switching frequency is switching frequency is 100 kilos. All the components can be assumed to be idle. The gate signals of switches S1 and S2 are shown in the figure. Average voltage across the 5 ampere current source is this, right? So okay, average voltage across the 5 ampere, average voltage across the, what is the average voltage across the 5 ampere current source? That is what they're asking. Okay, so they also have shown me when the switch S1 will be on, when the switch S2 will be on. Okay, and they have some reverse diodes as well. Okay, switching frequency is given to me, that is actually like at a certain point, if you see, right, both of them are off. Okay, so in this duration both of them are off, but still current is flowing, hence one of the diode must be on, right? One of the diode has to be on. Okay, if both of them are off, right, this is off, this is off, then who is taking this current actually? This is not possible. Okay, yeah, current will flow like this. Yeah, so this D2 will help the current to flow always. If both of them are off, D2 will help the current to flow. Okay, so when both of them are off, D2 will be on, and if D2 is on, the voltage across the current source is 0. If D2 is on, everything is idle, so voltage across the current source is 0. So when both of the switches are off, right, then voltage will be always 0 across the current source. So let me plot the voltage across the current source. So I will come to this 0 to 3. So let me first plot from 3 to 5. I think it is micro, right? Yeah, 3 to 5 microseconds. So from 3 to 5 microseconds, the current is 0. Okay. Then from 8 to 10 microseconds again, the current is again 0. Okay. Now what is happening? Now if you see that if this is on, right? If this is on, okay, when S1 is on, this is short circuited. So this comes here, this plus 20 volts comes here, and this minus point is always connected. So the voltage across the current source is plus 20 when S1 is on. So it is plus 20. So this is the voltage across the current source, whatever, V5 ampere, whatever you want to say. Now from 5, right, from the point 5 microsecond, S2 is on. When S2 is on, what will happen? Current, when S2 is on, right? Okay, when S2 is on, actually, uh, current can actually flow like this. Can it flow like this? No, current will not flow like this, right? So if S2 is on, will S2 on help in any shape or form? That is what I'm thinking. If S2 is on, current has to flow like this, current has to flow like this, and this current is flowing like this, right? How will S2 being on help me? So no, S2 is, if S2 is on, right, it does not help me at all. If S2 is on, it does not help me at all. If S2 is on, current can never flow through S2, right? Current has to flow through D2 only. So the voltage across S2 will be 0 only, and voltage across the current source also will be 0 only. And if S2 is on, right, if S2 is on, what will happen? This voltage will be, this will be reverse bias, because this is minus plus, this will be reverse bias, this will be off. This S1 also is triggered low. So okay, this is BJT, right? This is BJT. So okay, so this is plus minus, correct? So if it is triggered, this will turn on and all the current will flow through like this. So this potential is plus minus 20. As soon as it will trigger, this will turn on. This is, if this is turned on, both of them will turn on. If both of them turn on, they will be simply short circuited, and yeah, current will still flow like this, right here. So the voltage, bottom line is the voltage across this current source will be 0 actually throughout. So this will be 20 into 3 micro upon 10. So this will be 6 volt. So the average voltage across the current source will be simply 6 volts. Nothing to like worry about here, because it will always be 0 for the next 7 microseconds, right, till from here to here, because S2 being on does not help in anything. Okay, because ultimately the current will flow through D2 only. Yeah, let's solve the next question. So in DC to DC converter shown in the figure, the current through the inductor is continuous, so we can use all the formulas. So switching frequency is 500 hertz or 0.5 kilohertz, right? So your time period would be 2 milliseconds. Okay, the voltage VO across the load is assumed to be constant and ripple free. The voltage VO across the load is assumed to be constant and ripple free, so it is constant, that is 40 volt, right? So IO average will be equals to 4 ampere. uh, the peak current in amperes would be, what is the peak current? So for that I will actually need to calculate the ripple in the current, right? So once this switch is okay, I got my IO average. So do I know my delta IL, right? So once the switch is closed, right, have they given me anything? Okay, I know current is continuous, and this is a step up chopper. Okay, this is the figure of step up chopper. You can prove it. You can mark the inductor voltage. You can prove it. I am not in the mood of that. So if it's a step up chopper, right? So this will be so your VO over Vi would be 1 by 1 minus alpha. Okay, if you want to prove it, always happy, you can prove it. Okay, let's prove it. So this will be time, this will be VL. So when the switch is closed, the inductor voltage will be Vi. When the switch is opened, the inductor voltage will be Vo minus Vi. Okay, it will be something negative. Why? Because Vo is greater than Vi, as you can see. So although I'll write here Vi minus Vo, but it is negative, right? Because Vi is 20 and Vo is 40, so it is negative. So I can write here minus 20. I can write here plus 20, right? So, and I don't know this value. This is alpha into t, correct? Alpha into t, this is capital T, right? Now we can solve it. It's pretty simple. So this has to be 0. If it has to be 0, alpha has to be 0.5. This positive area and negative area has to be equal. It is symmetrical. So alpha has to be 0.5. That's it. So if alpha is 0.5, how do I calculate my VO average, right? So yeah, we got this value, but what is my what do they want? Oh, I got my alpha value. So from this, I got my alpha value to 0.5. From this also you can get your alpha value. So VO by VI, VO is 40, right? VO is 40. By 20, that is 2. So your 1 minus alpha equals to 1 by 2. So your alpha will be equals to 0.5. So in both cases you can get with formula, without formula. So alpha I got, but why was alpha required? Yeah, alpha was required to calculate this ripple, right? So when the switch will be closed, what will be the delta L, right? Delta L, I hope you know the plot of the current. Current will be somewhat like this, right? Then again current will reduce somewhat like this, right? That is what will happen. So okay, so what are they asking? They're asking me the peak inductor current, right? Peak inductor current. Okay, how do I compute the peak inductor current? So how do I compute the peak inductor current? So this voltage is always constant, correct? So will always this will always deliver 4 amperes of current, and there will be a huge inrush. Will there be a huge inrush of current? Let's see that. Okay, as soon as this switch will be open, right? So inductor will try to send the current that will change the voltage across the inductor, right? So that some current will flow, and that current will flow through the capacitor. That transient current will flow through the capacitor, and this current will always flow. What I am trying to calculate is the peak current. So the peak current will happen just before this switch is open, right? Because after that the inductor is delivering energy, the current will reduce. So peak current will happen in this region, right? At t equals to alpha into t, correct? Now, what is this IL minimum? Minimum amount of current. What is the minimum amount of current? What is the minimum amount of current? How do I calculate the minimum amount of current? Yeah, this I can actually, yeah, I can calculate. So what do I know? One more thing I know, right? There is no power loss. So what is input power? It is 20 into IS average. What is the output power? It is 40 into I average. 40 into 4. So IS average is nothing but your IL average only. So your IL average will be equals to uh, 8 amperes. Okay, IL average is 8 amperes, right? Now, if it is 8 amperes, right? So what do I know certainly? Certainly your IL average, uh, so your IL max, right? IL max will be equals to IL average plus delta IL by 2, because this thing has to be symmetrical, right? If I am not incorrect, this thing has to be symmetrical. I'm just trying to think why this will be symmetrical. Delta IL by 2, because your IL average will be always in the middle of your IL max and IL. This will always happen. Yeah, then only this cycle will keep on repeating. Otherwise, there will be some extra energy, right? That is not possible. So yeah, IL average will be like your IL average will be in the middle, right? So you can say that if it is in the middle, so your IL max will be IL average plus delta IL by 2. So I got my IL average. What is delta IL? So delta IL is pretty simple to calculate, right? So you know your VL is equals to L DIL by dt, correct? So your VL, voltage across the inductor when the switch is closed, it is 20, and your L is 2 milli, and your DIL is, that is what I have to find out, upon dt. Time is alpha into t. Alpha is 0.5, and your capital T is 2. Capital T is 2 microseconds, 2 milliseconds, right? So remember, it is 2 milliseconds, and this is also 2 millihenry. So that those will milli will be cancelled. This will be 1. So your delta IL is actually quite large. It is actually 20 amperes, right? So your delta IL is quite large, 20 amperes. So your IL max will be equals to IL average, that is 8 plus 10 ampere, delta IL by 2, that is okay. That is quite okay. Yeah, it will be yeah, 5 down, 5 up. Yeah, so it will be 8 plus 10. Am I correct? Hold on a second, let me check if I'm doing everything correctly or not. Alpha is 0.5, alpha is correct. Okay. Now delta L to, okay, sorry, this, okay, this is already 2 into 0.5, right? That is only 1, so this is cancelled out. So this is 10. Okay, sorry, this will be 10. This will be 10 amperes. If it is 10, this will be 10 by 5, 10 by 2, that is 5 amperes. So your IL max will be 13 amperes. This will be your answer. No formula will help you here. Okay, no formula will help you, but intuitions will help you. And this thing, yeah, this thing I used a formula, but it makes sense, right? So if my IL average is not in the middle, what will happen is, let's say my IL average is somewhere at the top. So every time, right, it will have more negative than positive. So next time, like this cycle will not repeat if this is not in the middle, right? This cycle will not repeat. Okay, this charging discharging will not happen, will not repeat. This has to be in the middle. This delta L has to be in the middle. Okay, so yeah, so for this 13 ampere will be the answer. Let's solve the next question. So this is the next question. In the circuit with ideal switches, the power MOSFET is operated with a duty cycle of 0.4. So duty cycle is 0.4, right? Your current is 10 amperes of the, what is the current? Current is, okay, input current. Yes, is 10 amperes. Your voltage, okay, output voltage is 15 volt. VO is 15. The power delivered by the current source. Okay, so when the switch is on, right? So this diode will be turned off. All of the current will flow through here. So no power will be delivered by the source at that point of time because the voltage is 0. When the switch is opened, right, all of the current will flow through this. Then the voltage across the current source is V only, right? So ultimately, what I need to calculate is, like, power delivered by the current source will be I average into V average. Right? I already know the I average because I average is always constant. That is I only. So it is always I only, right? And V average. So how do I calculate the V average? That is interesting. So if I calculate the voltage across the current source, when the switch is on, the voltage is always 0, 0.4. And when the switch is open, the voltage is simply V. Okay. This is 0.4 into T, and this is capital T, right? So the average voltage across the current source would be, this distance is 0.6 into T, right? So 0.6 into T into V upon capital T. So it is simply 0.6 into V only, and that value is given to me, right? So it is 0.6 into V. So it is, I is known to me, that is 10 into 0.6 into 15. So this will be 6 into 15, that is 90. So 90 watt is the answer basically, right? 90 would be your answer for the question. Okay, So let's solve the next question. So I guess this is the last one. Yeah, this is the last question. Choppers went long. So the steady state capacitor current of a conventional DC to DC buck converter working in continuous conduction mode. CCM basically means continuous conduction mode. They are also very lazy. They are not telling you that. Is shown in switching mode. Okay, capacitor current is shown. Okay, cool. If the input voltage is 30 volt, right? The value of the inductor used. Okay. Is DC to DC buck converter. So if it's a buck converter, right? The circuit diagram would be something like this. L, C, and here I have the load. Here I have the source, and the source voltage they have given me as 30 volt, right? Okay, so it's a buck converter. Input voltage is 30, and there has to be a freewheeling diode. Is it? So I can see the capacitor current is increasing from here to here, then it is reduced. So from this point onwards, the switch is opened. So capacitor is delivering. Okay. What is the voltage across the inductor when it is turned off? Suddenly the inductor current cannot go to 0, right? There has to be a diode as well, right? Otherwise it will not work. There has to be diode, because like the current across the inductor must be continuous, right? It is working in continuous conduction mode. So I need to put a diode, so when the switch is open, so whatever current it has, it will flow like this in this path. Okay, now the circuit is complete. Now I know the capacitor current. So we know that in this duration when the switch is on, it is charging. Capacitor current is increasing, so of course it is charging, right? So the capacitor voltage is constant here, and as soon as the this switch is turned off, the capacitor voltage is negative. Okay, so the load voltage also will change then. Okay, load voltage also will change. That is interesting. Capacitor current is shown. So how do I solve this? What of the value of the inductor used? C dVs AVDC equals to IC. This is the current, right? Capacitor current. So whatever ripple you see, right, in the capacitor current, whatever ripple you see, this same ripple will be exactly carbon copied to the inductor current. Okay, so inductor current will have some average value, as I said, mentioned in the previous question, and it will have this ripple. So the ripple will not be there in the load current. Load current will be constant. That is our assumption, right? So it will have some average current, and this will be minus 0.1 to plus 0.1. So basically this will be my IL average, right? And your delta IL, right? Your delta IL will be equals to 0.2 amperes. This is the information that I need. Okay, that's enough. We got our solution. Okay, that's enough. Now what is the duration from 0 till this duration? I don't know, but I do know that to go from 0.1 to 50 0.1 to 0, right, it took 15 microseconds, and this slope is not changing. So it will take another 15 microseconds to reach from 0 to 0.1 plus 0.1. So overall this is 30 microseconds. 30 microseconds. Okay, now uh, again it will reduce. I don't care about the reduction. The slope is different here. All I care about is this. Actually this is not symmetrical. It will reduce at a faster rate because it is reducing earlier, right? Now I got my del IL, and if the inductor is there, once the switch is closed, right? Okay, I'm missing something. It seems like that. If the switch is closed, then there will be current across the inductor, but I don't know the load voltage. They should have given the circuit. They have given the input voltage is this, simple buck converter. So once the switch will be opened, the voltage, how will I be able to comment about the voltage? Not be able to comment about the voltage, right? Will I be able to comment about the voltage? I think we will. Huh. So what happens? Mm, no, nothing is given, right? How will I comment about the voltage? LC del L is 2. It is a buck converter, right? Buck converter is this only. Just thinking, I'm thinking if there is any other way. Okay, actually I may have drawn it wrong somehow. I think this is the correct way to draw it, but that also will not work, right? This is good. LC filter only, this is correct. Okay, we can use this actually to our advantage. IC equals to CD, so I did if I integrate this, that will be direct change in the voltage, right? But I don't care about the change in voltage. So what we can assume the voltage to be also constant here. Let's say this is VO, right? So during the on process, so what is the voltage across the inductor? VL. So this will be when the switch is closed, right? So it will be 30 minus VO. So it will be 30 minus VO, and when the switch is open, right, simply this diode will be turned on and the inductor voltage will be minus of VO, right? This is plus minus VO. You can apply key VL and you will get minus VO. Okay, and this time is 30 microseconds, right? And the end time, right, end time actually we need, that is 50 microseconds. This end time is 50 microseconds, and it is operating in continuous conduction mode. So this area of the inductor voltage must be 0. That is 30 minus VO into 50. So not 50, 20, right? This width is 20 micro. Okay, don't forget to multiply the duration. 30 micro, 20 micro equal to 0. So from here this will be 90 minus 3 VO minus 2 VO equal to 0. So your VO will be equals to 18 volts. VO will be equals to 18 volts. Okay, that is my VO average. Now this VO will actually help me to compute the inductor. How? So we can use any equation. So this del IL is always same, right? This is 0.2. So either I can use this duration or this duration. So I will use the first one. So we know in this region, right, what is the voltage across the inductor? It is 30 minus VO. So it is 12. VL will be equals to L DIL by dt. Okay. So L will be equals to I don't know. L is what I have to find out, right? Into into DIL, right? DIL by dt. So what is the change in current? That is 0.2, right? What is the change in time? It is 30 microseconds. 30 microseconds. 30. This micro. So L also will be in micro only. But what have they asked? They have asked me in milli. So let me convert this in milli. Actually, this will be 3 into 10 raised to power uh, minus 3 actually. So this minus 3 will go there to convert this into milli actually. So what will happen is this is 5. So 60 into 30 into 10 raised to minus 3 is equals to L, right? So L will be equals to 1800, that is 1.8 millihenry. Okay, so 1.8 millihenry will be your answer. Question was pretty simple, just that you have to pick up that the voltage will be constant. Okay, uh, and why will the voltage be constant? Because like continuous conduction mode, right? Voltage, current, all of them we have to assume that they have to be constant. Okay, so yeah, so like this you can solve, you can put this in repeat, and with this we end our choppers. Now we will start with our inverters chapter. So let's start with inverters, and in inverters unfortunately is the one uh, chapter in power electronics that I will say mostly you will have to remember certain things, right? So please go through the revision X notes and see what are the important formulas, make a note of them, remember them, because those will be bit important. And like power semiconductor switches and inverters, these two chapters are the chapters that I will say to most students that you might have to remember stuff. In rectifiers, in single phase rectifier, you will very rarely have to remember. We have solved all the rectifiers with basics without remembering much formulas. Choppers you have seen, like I've hardly used any formulas, right? We have always tried to solve every question by basics. But inverters is one chapter that if you try to solve with basics, it will be a mess up. It will take too much of time. So you'll not be able to solve with basics. You'll not be able to do the complete analysis there. So I will quickly uh, uh, emphasize again that please go to the revision X notes, revise those, then come back. If you don't revise, if you come back here directly, you will not be able to solve most questions, because most questions will involve bit of formulas that you need to unfortunately remember. And the point of revision is you don't go back to your notes while solving the question, right? You go back to your notes before solving the question, and while you are solving the question, you are solving with your brain. Yeah, so let's start. This is the first question. The output voltage of a single phase full bridge rectifier. So it is a single phase full bridge rectifier. Single phase full bridge rectifier uh, is controlled by unipolar polar pulse width modulation. Okay, so what is unipolar pulse width modulation? With one pulse per cycle. So per cycle there will be a pulse. Uh, so in unipolar pulse width modulation, what happens? Like we get a pulse like this. Okay, this is called as single. It is also called as a single pulse width modulation. Okay, and for they are asking me for the fundamental RMS component of output voltage to be 75% of the DC voltage. So it's a full bridge inverter. So for a single pulse width modulation, right, the output voltage is somewhat like this. Okay, and this particular thing is known as the pulse width, right, also known by D. Okay, and the Fourier series expansion of this particular waveform, like it is not pure sinusoid, but it is very close to sinusoid. The Fourier series coefficient is this, and this is what you have to remember. Okay, this whole thing you have to remember, and this is already present in revision X notes. If you don't remember it, you will not be able to solve it. Simply they are asking the required pulse width in degrees will be. So you know what is the sinusoidal expansion, and they are asking me that the RMS fundamental RMS component. What is the fundamental RMS component? So it will be n equals to 1. N equals to 1, this will be 4 VDC upon pi into sine, where n equals to 1, this is sine pi by 2, that is 1 sine nd that is sine d only, right? D, where D is the pulse width basically. So that is what they are asking. What is the pulse width in degrees? Okay, and this is the amplitude. They are talking about the RMS. So I have to divide by root 2. This is the RMS, right? VO1 RMS, correct? Your RMS value is 75% of the DC value. So it is 75% of the DC. Basically, this is equals to 75% of DC, that is 0.75 of VDC. Okay, so yeah, so from here we can directly say what is sine D. Sine D would be equals to 3 by 4 into root 2 pi by 4. That's all. So let me solve it. If I solve it, right, this will be 3 into root 2 into pi upon 16. So that is sine D comes out to 0.833, and if I take the sine inverse of this, So D will come out to be 56.41 degrees. Now question is pretty simple. Okay, but the only problem is you will have to uh, remember the formula. Now okay, one short thing, right? One short thing. Okay, I missed a point here actually that is not present in the this notes. Okay, sorry. So actually what happens is this part is actually D. Okay, this point was missed in the question. This part is D. Okay, and your pulse width is actually 2D. So this point actually I believe it is missed in the notes, or maybe it is present in the notes. I have to check. So this is the half width actually. D is not the pulse width. Pulse width is 2 into D. Okay, so a few things you have to keep in mind here. If you don't keep in mind, then you will just mess up. So your pulse width, right? This is D. D is the half width here in this formula. So pulse width will be equals to 2 into D. So 2 into D would be simply multiplied by 2, that is 112.824. So these things you have to keep in mind. These are actually pretty important things. Okay, so if I they're asking me round up to one decimal place. If I round up to one decimal place, it will be 112.8 only degrees. This will be the answer. Just be careful. Let's solve the next question. So next question is also related to uh, like the same waveform only. So if you see, this is the exact same waveform, right? So single phase voltage source inverter is fed from a 100-volt DC source. So as you can see, plus VDC minus VDC, and it's controlled using Cauchy square wave modulation scheme. So the waveform that you get is same, this waveform only. Now VT is shown. The angle sigma is adjusted to entirely eliminate third harmonics component of the voltage. Under this condition, Vt, the voltage of the fifth harmonic as a percentage of the uh, magnitude of the fundamental component. So basically, they are asking me that they have given me this information that VO3 is 0. Okay, and they are asking me the ratio of VO5 upon VO1 as a percentage. Okay, into 100 percentage. Now, again, this will have the same formula, right? And they're telling me that this particular thing is gone. What is gone? Your third harmonic is absent. If your third harmonic is absent, right, this is, if n equals to 3, right, this is sine 3 pi by 2. So this is 1 only, no problem. Which what factor can make the third harmonic absent if this goes to 0? So when my sine 3d equals to 0, my third harmonic will be absent, right? So what does my d needs to be? So d can be 60 because sine 180 is 0. So if d is 60 degree, then my third harmonic will be 0, right? Because sine 180 is 0. Okay, because why 3d? Because I have third harmonic is 0, so n equals to 3. So that part is clear. Now, now what you have to do is you will have to put this in the, so I know the d. So this is the d, right? My d is 60. But they are asking me in terms of so what are they asking me actually? So I don't care actually. I don't care what if they have given sigma or something. I have got my d. All they want is magnitude of the fifth harmonic to the fundamental. I can calculate that. So what is the fifth harmonic to the fundamental? So it will be VO5. I don't care about sigma and all those things, right? I know my formula. So VO5 upon VO1 into 100. This will be equals to magnitude. They are telling me it does not matter if it is negative or positive. Okay, so I have to take the magnitude. So magnitude of VO5 upon magnitude of VO1. So this will be so all these things will be cancelled actually. 4 VDC upon pi, these are same numbers, right? This will be cancelled. This is the fifth harmonic, so 5 will be there into sine 5 pi by 2. So what is sine 5 pi by 2? Okay, few things might change. So sine 5 pi by 2, right? So sine 270 actually. Okay, so yeah, there is a difference of sign actually. Yeah, this will not always be 1. There will be a difference of sign. Sign meaning either it will be +1 or -1. That's all. So if I see here, sine 270 is actually, it is -1, and we're doing 5 times this. So sine 5, 19 to 5, sine of this, it is 1. So this is 1 as well, and this is also 1. So sine 5 pi by 2 is 1, sine pi by 2 is also 1. So this is 1 and this is also 1, so it won't matter ultimately. 4 VTC upon pi upon 4 VDC upon pi into 1, then into sine nd, right? Sine nd, sine into n, that is a fifth harmonic, into d is 60 degrees, right? Upon sine d, that is 60 degrees, n equals to 1. So this is the ratio, and sine 300, I am guessing that it will be something positive only, so no problems. This ultimately we have to find out this ratio, this and this. Everything else will be cancelled, right? So this 5 will be there, so there will be, and obviously don't forget into 100 percentage, because we have to calculate in terms of percentage. So this will be 1 by 5, and this will be sine 300 is actually 0.5. Sine 60 is also, okay, no, sine 60 is root 3 by 2 actually. So it is root 3 into 0.5, correct, into 100. So this will be 20 upon root 3, 20 upon root 3, that is 11.54 percentage. Okay, so yeah, this will be your answer basically. 11 point, so they are asking me the magnitude of the fifth harmonic. Yeah, this will be the answer, 11.547 percentage. Yeah, just a small mistake on my behalf. So sine 300 is actually not 0.5, it is actually same, right? This is also root 3 by 2, but this is minus root 3 by 2, but they have anyways asked us to calculate the magnitude, so it won't matter ultimately, right? So root 3 by 2, root 3 by 2 will be cancelled, so ultimately the answer will be 20%. So that there was a small mistake on my behalf, this will be 20%. Okay, so yeah, we're done with this question. Let's now move on to the next question. This is the next question. So a single phase full bridge rectifier uh, is fed by a 325 volt DC, and we have a quasi symmetric waveform. So this waveform is actually pretty important. The Fourier series of this waveform, right, is pretty important. So this has been asked multiple times in the past years, right, and maybe asked in next years as well. So this waveform is pretty important. You must remember this waveform. Okay, here what they're telling us that uh, so they are getting this quasi waveform to achieve this of with a modulation index of 0.8. The angle theta expressed in degrees must be what? Okay, so modulation index is 0.8. What does modulation index means? Basically this modulation index gives me the, so here, right, the peak value of my fundamental component. Okay, this is the fundamental component. Peak value of the fundamental component is equals to the modulation index into the DC value. This again is a result that you have to remember. This, there is a derivation, but we don't have time for that. So here, whatever is the fundamental component, this fundamental component must match with this fundamental component, correct? So what is the, to achieve this to achieve a modulation index of 0.8? So if modulation index is 0.8, so what is the peak value of the fundamental component, right? Vm1, it will be Ma into VDC. Ma into VDC is 325, correct? 325 volts. Now this is the peak of the fundamental component, right? And this peak should match with this one. So what is the value of theta that they have asked? So how are they defining the theta? Be very careful. So they are defining the theta like this, right? This is my theta, but I define it always in terms of this, right? Like you should remember both the formulas. So this, right, there are two formulas. Either you can write this cos n pi by 2 minus d. So this pi by 2 minus d is nothing but, so this is my this width is d, right, and this whole thing is pi by 2. So this much will be actually pi by 2 minus d, this distance, right? That is nothing but my theta in this case. Okay, so there are, like, these two are the saying the same things. So if you expand this, what you will see, you will get cos a cos b plus sin a sin b. So cos a cos b will be 0, because cos n pi by 2 will always be 0. That's why you will only get sin a sin b. So this is the simplified formula, that's all. So either you can use this formula or use this formula, it does not matter. Yeah, but I think it's good to know both of them, because you don't know what will come in handy. Now here they have told me that the peak value must be this, right? So here what is the peak value for the fundamental component? It is 4 VDC. 4 VDC. So let me write this VDC only, right? VDC only. Yeah, 4 VDC upon pi sine of pi by 2, that is 1 only. Sin of t, that is equals to 0.8 8 into VDC. So this will be gone, this will be gone. Sin pi by 2 is 1. So your sin d is equals to 0.8. Or I can say like 4 is there, so 0.2 by pi. That is what my sin d is equals to. Sorry, not by pi, 0.2 into pi. Okay, so 0.2 into pi sin inverse. So that is my d. Remember, this is not my theta. So my d is actually 38.926 degrees, but they have asked me theta in degrees, right? Theta in degrees. So theta is nothing but, so this is my d, right? So theta would be pi by 2 minus d. So this pi by 2, that is 90 minus d. So, or I can say 90 minus d, right? So that would be equals to 51.07 degrees. Okay, so 51.07 will be your answer for the question. So yeah, mostly questions will come from this quasi sinusoidal waveform only. Not quasi sinusoid, quasi square wave. Let's now move on to the next question. So consider an ideal full bridge single phase DC to AC inverter with a DC bus voltage magnitude of 1000 volts. The inverter output voltage Vt shown below is obtained when diagonal switches of the inverter are switched to 50% duty cycle. Okay, so there is 50% duty cycle, as you can see it is a full base inverter, and VDC is 1000. So this will be basically plus 1000 when the first half will be switched on, and the other half when they will be switched on, it will be minus 1000. The inverter feeds a load with a sinusoidal current. I of t is this. The active power delivered to the load is, what is the active power? So the inverter feeds to a load whose current is given by this. What is the active power? Now remember, current is given, right? So if current is given, I already know the Fourier series expansion. This is the load voltage, right? Of the load voltage. This will be, this I know. Okay, this anyways you have to remember. This is 2 into peak to peak, right? So 2 into peak to peak. Peak to peak is 2 VDC by n pi sine n omega naught t. Okay, there is no phase shift here, right? Now the interesting thing that will happen is, because my current has only a single frequency component, the voltage, the power, right, will be only due to the fundamental component, because there is no other component of frequency in the current, right? I can write this omega. So yeah, that's basically it. That's basically your solution, right? So what will be your power? Your power will be VO1 RMS, because you have to consider the fundamental component. So that is 4 VDC upon root 2 into pi into IO RMS, that is 10 by root 2 into cos of pi by 3. Cos of pi by 3, the phase difference between the voltage and the current, right? Cos of pi by 3 is cos 60, that is half. And VDC is 1000, so it becomes very simple and easy to solve. So this will be 4 into 1000 into 10 divided by 2 divided by pi into 0.5, and they have asked in power in watts. So this will be a large number, which is 3183 watts. Okay, round off to nearest integer, 3183 would be the answer for the question. Let's now solve the next question. So yeah, this anyways you remember this thing. This is a pretty simple question that they will ask. Next question. This is again a pretty interesting question, and again for this you will have to remember a result. Okay, there is a result. This unfortunately you will have to remember. So a three-phase grid voltage source converter with the DC link of 1000 is switched using pulse width modulation technique. Okay, so VDC is 1000 volts, right? And we are delivering three phase grid, three phase. if the grid phase current is 10 ampere, so phase current of the grid, right, is 10 ampere, okay, and three phase complex power supplied by the converter is minus 4000. That's interesting. That means it is absorbing power, not delivering power. Minus J 3000 active power I'm talking about. Then the modulation index used in the sinusoidal pulse width technique would be equals to what? Okay, so nothing is mentioned. You will assume it to be star load, and they have given you the power. From this power you will be able to calculate what? You will be able to calculate the line voltage. So you know what does so what is my apparent power? So apparent power would be simply your magnitude of 4000 plus magnitude of 3000, that is 5000 under root, that is 5000, right? So this will be equals to this is the three phase power, this will be equals to root 3 into VL into IL, right? Now here the interesting fact is, like, in we will assume obviously star connected load. So in star connected load we know the line current is same as phase current, right? So we will get our uh, V line will be 5000 divided by root 3 into I phase, that I line, that is 10. So it is basically 500 divided by root 3, that is 288.67. This is the RMS value, okay? V line RMS, this is all RMS. V line RMS volts. Now here what you need to do is what is given to you, right? What is given to you? There are a few things that you have to do. So in sinusoidal pulse with modulation, what happens is, in three phase sinusoidal pulse with modulation, your line to line voltage, the peak value, right? This is the peak value. They are talking about the peak value. The peak value is actually equals to uh, root 3 MA into VDC. Okay. Now this will not be VDC by 2 because it is a full bridge inverter. I think they have mentioned. Is it a half bridge inverter or a full bridge inverter? DC link. The converter is given by this. Okay, nowhere it is mentioned. That is very weird. So three phase grid connected voltage source converter. Okay. Actually, they should mention it, whether it is a full bridge inverter or half bridge inverter. Nowhere they have mentioned it. That's pretty bad actually. So this question is not complete. So by default, you will assume half bridge inverter, but trust me, like, this question will not come now, because uh, again I feel like they should have mentioned, right, whether it is a full bridge inverter, half bridge inverter. At least draw the circuit, do something. You don't say anything. How will the student understand whether it is a full bridge inverter or a half bridge inverter, right? You will not be able to figure out it. So yeah. Uh, so assuming half bridge inverter, so your peak voltage will be root 3 by 2 this, right, into VDC. This will be equals to 288.67 into root 2. So VDC I already know, 1000 volt. So yeah, 1000 is there. MA would be equals to 288.67 into 2 by 3. 2 into root 2 divided by root 3, that is okay, and obviously divide by VDC as well, right? Don't forget to divide by VDC as well. So divide by 1000. So this will be MA will be 0.471. Okay. So yeah, the only thing that I can discuss about this question is they should actually mention that it is a half bridge inverter, otherwise students simply will not be able to understand it, right? Okay, so let's solve the next question. So next question again, it is a single phase full bridge. Here they have properly mentioned it is a full bridge inverter, right? Here nowhere they have mentioned whether it is a half bridge or a full bridge inverter. By default, if nothing is mentioned for three phase, you will assume half bridge, but they should actually mention it. Yeah. So a single phase, so this question was during my time, so I was not able to solve it. Single phase full bridge inverter feeds a purely inductive load. The inverter output voltage is a square wave in 180-degree conduction mode. Okay, so basically the square wave is somewhat like this, right? Like this is the output voltage, and this will have, this will be T by 2, this will be T at 180-degree conduction mode. If the DC input voltage is 100, so this will be plus 100 plus 100 and minus 100, right? And the load inductance is 20 millihenry. The peak to peak load current will be, what is the peak to peak load current? So what happens, so the load is purely inductive, right? So I have a load that is purely inductive, and the voltage from 0 to T by 2 is always constant and positive 100, and from T by 2 to T it is always constant and negative 100, correct? So what will happen here is that, if I assume a symmetrical case, right, so current will start from negative peak at equal to 0, because it is plus 100 it will go to plus positive peak, because we have seen this, we know this graph, right? We know what happens, it is triangular kind of thing, and as soon as this negative will come here, right, again the current will start to reduce. Okay, and it will start reducing till capital T. And so on, correct? What are they asking? They are asking me this peak to peak value 2i. I can easily calculate this 2i, right? So simply I can use, I don't like, here we don't need to use any formulas, so it will be delta, so basically VL is equals to L DIL by dt. So what is the voltage from 0 to T by 2? It is 100 across the inductor, that is my load, into L. L is 20 millihenry into delta L, that is what I have to calculate, right? I have to calculate the peak to peak difference. Okay, peak to peak load current, and assuming your time also in milliseconds only. So 50 hertz, 50 hertz basically means 20 milliseconds, correct? 20 milliseconds. So T is 20 milliseconds, but this duration is T by 2. So this will be 10 milliseconds. So this will be 10 milliseconds. So milli will be cancelled, right? Millihenry and milliseconds will be, milli will be cancelled. So this will be 2. So delta L will be simply 50. Delta L will be 50. So 50 will be your answer for the question. Not that difficult. So although there is like this derivation, we have made this derivation, but we don't need to understand, like we don't need to remember the formulas here in this case, because we can simply solve it without any formulas. Okay, I hope that makes sense. So 50 was answer for this question. Let's now solve the next question. I think that is the last question that we have. Okay, so three phase modulating waveforms are shown VA, VB, VC using sinusoidal pulse width modulation. Omega is this, is the fundamental frequency. The modulating waveforms compared with are compared with a 10 kilohertz triangular carrier wave whose frequency, whose magnitude varies from +1 to -1. The voltage source inverter has a DC link VDC of 600 volts. It feeds a star connected load. Okay, so load is star connected. The per phase fundamental RMS motor voltage will be, okay. Okay, three phase modulating waveforms. Okay, these are the three phase modulating waveforms. Okay, used in sinusoidal pulsation are this VA, VB, VC. Okay, modulating waveforms, three phase modulating waveforms are this, and okay, these are the three phase modulating waveforms whose magnitude varies from +1 to -1, are compared, the modulating waveforms are compared with a uh, triangular carrier. Okay, they are compared with a triangular carrier. So if they are compared with a triangular carrier, right, if you remember that there was a formula. So here we mainly have to calculate the uh, modulating index. Okay, and how do I calculate the modulating index for a triangular carrier, right? The modulating index MA is basically equals to the uh, peak of the phase modulated waveform, that is AM, upon the peak of the triangular waveform. That's all. So my triangular waveform is modulating this. Again, you can follow the revision X notes. There we have discussed how this derivation comes. Like it's a very lengthy one, so we'll not be able to go over it. But AM by AC will be my modulation index. In this case, AM is 0.8 and AC is simply 1, right? The peak of the triangular waveform, it is 1. Okay, so we got our modulation index. So the per phase RMS fundamental motor voltage. So per phase RMS fundamental motor voltage will be basically, so we know the VO1 maximum, right? VO1 maximum. Again, nothing is mentioned per phase. They're asking me phase, right? Phase, for phase we'll use this particular thing, right? VO1 peak. This is the full bridge inverter. What is it? Have they told us what kind of inverter it is? Again, nothing is mentioned, right? Again, they should mention. I don't understand why they don't mention. It is only a voltage source inverter, so we'll assume it to be half bridge inverter. Nothing is mentioned. You'll assume it to be half bridge inverter. So this is my modulation index. So the VO1 peak will be MA into VDC by 2. Okay, by default, if nothing is mentioned, you'll assume it to be half bridge inverter. MA is 0.8 and VDC is given. VDC is 600 by 2. That's 300 into 0.8. That is my 240, right? Now this is my peak value. They've asked me the RMS. What is the RMS value? RMS value would be divided by root 2, correct? So VO1 RMS will be this divided by root 2. So this shall be 240 divided by root 2. That is 169.71. And they have not given like the double answer of this. So that means they are referring to half bridge inverter only. They are not referring to full bridge inverter. So otherwise, times 2 would also have been present in the options. So that's how you solve this question. So inverters questions will not take much time, but you have to remember the formulas. That's all. So inverters is a bit tricky in that sense. So with that, we have finished with power electronics. I hope you have enjoyed this whole thing, right? You have revised a lot of concepts here, and I hope you understand where exactly you lack, and you can actually go to those places. You can use our revision X notes or any other place, right? You can go and revise through those notes. So that's all for this video. If you have enjoyed, again, like the video, hype the video, share the video. That will help us out a lot. Thank you and happy learning.